Hi, everyone, and welcome back for day 2 of the Platform for Situated Intelligence workshop. I hope you enjoyed all the sessions yesterday, and we've got some really great stuff lined up for today. But first, let me review a few of the mechanics. We are recording these sessions, and we'll make all of those recordings publicly available within a week or two after the event wraps up today. So if you miss anything, if you missed anything, if you encountered any technical hiccups in the stream yesterday, we're sorry about that. But please check back to the event website for the recording soon. All questions in Teams Live can be submitted through the chat tool. You can submit questions at any time during the talks, and we really encourage you to do so at any time during the talk. But we should also have ample time for further Q&A after each presentation. Please feel free to let others know about this event and about the framework itself and amplify it on your own social media channels. You can use the Sci open source hashtag if you wish to do so. And lastly, we will be sending a post-event survey after the workshop concludes today. And we'd really appreciate it if you could take 3 to 5 minutes and complete that survey for us so we can better gauge your interests and improve on future events. Okay, so today we have a great lineup of sessions, including some deeper dives and more technical walkthroughs of special topics, including how to interoperate with various other ecosystems, and also preview some demos of new stuff we've been working on. So let me just do a quick preview of all the things you're going to see today. So we'll kick things off with a presentation from Nick Saw on how to use some of the powerful affordances and tools in the Sci framework for collecting diagnostics information on your Sci pipelines and debugging them. And visualizing diagnostics info like you see here can be super helpful for debugging issues as your applications grow in scale and complexity. And Nick is going to walk through a few different common debugging scenarios. In the next session, Ashley Finello will present an overview of interoperating between Sci and other programming languages in general, but particularly focusing on Python. He'll describe our cross-process messaging infrastructure and do a hands-on coding session from scratch, bridging media capture in Sci with face detection in Python. Then, after a quick break, Ashley will be back to talk about another interop scenario, this time with ROS. So Ashley's going to talk about how you can construct hybrid systems that leverage both Sci and ROS. And he'll again go through a full coding example showing how to connect the ROS turtle sim with a simple Sci application that will be used to drive the virtual turtle around. So after those more detailed technical sessions, we're going to go into a few more high-level sessions showing off previews and videos of some cool new stuff coming down the pipe. So Dan's going to preview an upcoming feature on interoperating with the HoloLens 2 device, which is the mixed reality headset from Microsoft, including a large number of sensors, producing a large number of multimodal data streams. And Dan's going to showcase a simple app we've built where we use a ResNet image classification model together with Azure Translator Cloud Services to place augmented reality post-it notes on objects in the world to display each object's name in a different language. After that, I'm going to preview an upcoming feature which enables you to combine Sci with Teams. In particular, I'll be talking about how we're able to integrate a Sci pipeline inside a Teams bot architecture to process video and audio streams from all participants in order to prototype intelligent meeting experiences. So here we're going to show a simple demo sample on how you could use a Sci Teams bot to show a little bouncing ball that tracks the most dominant speaker or scales the video thumbnail of the most dominant speaker at each point in the meeting. And then finally, our last session of the workshop will be a preview of a higher level framework of components, representations, and inference models that we've been building on top of Sci called Situated Interaction Foundation, or SIF. We're developing SIF to promote more research and development of physically situated interactive systems, which are these systems that can reason about and act within a physically situated context and interact with and around groups of humans in the world, like social robots and embodied conversational agents. So that's just a quick preview of what you'll see today. I hope you stick around and chat with us throughout these sessions. We're excited to discuss all these topics further with you and answer any questions you might have along the way. But next up, we'll just go right into Nick's presentation on debugging and diagnostics. So let's go to that now.
In this session, we'll look at techniques for debugging Psi applications and some of the tools the framework provides for supporting and accelerating diagnostics and debugging. As always, feel free to type any questions or comments you might have into the chat at any time, and we'll either answer them directly in the chat or in the live Q&A portions, which we'll have time for midway through and at the end. As we discussed yesterday, Psi is a framework that helps accelerate the development of multimodal integrative AI applications. These applications often have particular characteristics that make problems more challenging to debug and diagnose when they arise. For instance, they tend to use a heterogeneous set of component technologies such as sensor-specific SDKs, cloud services, custom components, deep-net models, and more. The data is continuously streaming in real time, and the computation is typically parallelized and carefully coordinated over many components. Diagnosing problems in this sort of concurrent multi-threaded streaming environment is not practical with common debugging tools and techniques such as breakpoints and code stepping. In the course of our work developing these kinds of systems, we've found that having an aggregate view of the running application can be invaluable for identifying and diagnosing problems. This helps by providing an overall view of the pipeline structure, which can oftentimes be quite complex, as well as insights into the flow of data through the application at a glance. Psi comes with diagnostic visualization tools that let you inspect the application's pipeline structure and view statistics characterizing the flow of data through the application to identify problems quickly. In this session, we'll introduce you to the visual tools that Psi provides to let you quickly and intuitively diagnose problems in a Psi application. Then we'll show you some techniques for using these tools to solve a couple of simple but nevertheless common problems that may be encountered in Psi applications. One in which messages appear to stop flowing, and another in which we observe ever-increasing message latencies. In the process, we'll introduce two other core Psi constructs, the join operator for fusing streams and delivery policies. So let's start with a brief introduction to the tools. We'll use the Azure Connect sample application throughout this session as an example to show you how to use the diagnostics tools in Psi. You can find the sample at the Psi samples repo. This sample is a simple demonstrator of how to use the Azure Connect sensor to capture video from the camera and fuse it with body tracking. Opening the sample in Visual Studio and running it, we see that it captures the camera image from the sensor and renders it as ASCII art in a console window, with the head joint position from the body tracker highlighted as a small red dot above. Taking a closer look at the code, we can see that what it boils down to is it creates and configures an Azure Connect sensor component, then applies an image resize operator to the color image stream, uses a couple of join and pair operators to fuse various sensor streams together, then renders the composited image inside a do operator here. We'll talk about the join operator in more detail later on, but for now all you need to know is that the join and pair operators provide different ways of fusing streams in Psi. And this is just a block diagram of what the constructed pipeline looks like. As I mentioned, Psi provides tools that allow us to collect and visualize various diagnostic statistics about a pipeline. So let's take a look at how to enable that. To enable diagnostics on the pipeline, you simply need to set the enable diagnostics parameter to true when creating the pipeline. This tells the pipeline to collect various statistics while it is running and publish this information on a regular Psi stream. Now that's pretty much all you have to do to enable diagnostics. However, Psi also allows you to configure various aspects of diagnostics, which we will do here by creating a diagnostics configuration object and passing that to the pipeline create method as well. Remember, this is optional, but for this example we need to enable the track message size option, and we'll see why a little later on. In order for us to actually view the diagnostics later in Resize Studio, we need to save the contents of this stream. We will write the diagnostics stream to a Resize store, which we are creating here. Here you can see the pipeline diagnostics stream, which we will write to the store we just created. We'll name the stream diagnostics and write it to the store. And that's pretty much it. All we need to do now is run the application again. And the application's running, and we can see the same ASCII art rendition of the camera image. That's me waving at you again here. Now, while the application is still running, if we switch over to Resize Studio and open the store that the application is writing to, we see that a diagnostic stream is persisted in the store, capturing information about the overall pipeline, the state of each component, and statistics regarding the flow of messages. This stream may be visualized and inspected in Resize Studio. And I'm just changing the layout orientation here to vertical so that we can see things a bit more clearly. Here you can see that as the pipeline's running, these numbers are updating in real time. We'll go into more detail on what these numbers all mean in just a little bit. And of course, the store may also be opened in Resize Studio after the application has finished running. We can load the saved store and visualize the diagnostic stream again. We can scrub over the application timeline to get a view of the pipeline and statistics over time. Now let's take a closer look at the diagnostics graph. So here in the visualization panel, we see a graph representing the application pipeline. Each node in the graph represents a component or stream operator, and the edges represent streams over which messages flow between components. In this simple example, the graph is fairly compact, but in general, a SI application typically contains many more nodes. Here we see the Azure Connect sensor component, and each join and pair operator on a stream is represented by a node. Several simplifications are used to unclutter the graph. For example, certain types of nodes representing common components are denoted by small symbolic icons rather than a labeled graph node, such as this plus sign for the join operator. This component here represents the built-in exporter component, which is responsible for writing streams to disk. Recall that in this example, we are writing only the diagnostic stream, but in general any size stream may be written to the store. Enabling diagnostics creates another built-in component, the diagnostic sampler. Note that there are no edges on either of these two components. This is because of another simplification which hides all the stream connections to the exporter. If we were logging many streams, all the edges going into the exporter would clutter the graph view, so they are hidden by default. We can unhide them by checking the Show Exporter Links checkbox in the Diagnostics Properties panel. In this case, there is only one persisted stream produced by the diagnostic sampler, so only that stream goes to the exporter as shown here. Now let's take a look at some of the other diagnostics visualizer properties. Visual properties of the graph may be changed here in the Properties panel. For instance, you can change the node color, edge thickness, and graph layout direction to make it easier to view depending on the structure of the pipeline. You can also zoom in and out and pan around using the mouse. Remember that Psi lets you organize components hierarchically into composite components or subpipelines. Such composite components, like this Azure Connect sensor, are highlighted in blue. We can double-click on a composite component to reveal its internal structure. This brings us from the application's top-level graph into the internal sub-pipeline graph of the Azure Connect sensor component. Notice the breadcrumb navigation bar here that shows us where we are and enables us to navigate back up the hierarchy. Here, this reveals that the Azure Connect sensor aggregates two other components: a core source component, highlighted in green, which produces many sensor streams, and a body tracker component, which uses the depth and infrared data to perform body tracking. As we mentioned earlier, when diagnostics are enabled, the SAI runtime records a variety of statistics about the flow of messages through the pipeline. For instance, by default, the edges display information about message latencies. Clicking on an edge brings up a panel displaying various other statistics collected about the selected stream. These include the type of messages, delivery queue information, and other message statistics. Note that many of these statistics are presented as both instantaneous last values reflecting the state at any given point in time, as well as averaged over a configurable sliding time window. Clicking again on the edge hides the panel. You can also change the default statistic that is displayed on the edges by choosing from one of the available statistics in the Properties panel. Statistics displayed in the Information panel update as you navigate over time in SAI Studio or in playback mode. This allows the user to gain an understanding of the behavior of the message flow at different points in time over the life of the application. Where diagnostics really shines is by providing insights into system-wide behavior at a glance. The graph may be configured to show a colored heat map based on any selected statistic. Note that the edges are annotated with a label and a value. The label may be configured via the Properties panel to display emitter or receiver names, or indeed both. The value in parentheses represents the currently selected heat map statistic, in this case the average message latency. This may be changed using the drop-down property setting. The information is useful for getting a high-level view across the entire pipeline as to how the streams are behaving with respect to the currently selected statistic. For example, selecting message latencies here, we can quickly see by the edges colored in red that the majority of the latency in the system, greater than 500 milliseconds here, is downstream from the body tracker component. This suggests that the body tracker is taking a longer time to process messages, so its resulting output messages have a proportionately larger latency. Highlighting the message processing time statistic confirms that the body tracker consumes the majority of the time. Since computing body joint positions from the depth and IR images is a fairly computationally intensive process, this is not entirely unexpected. Let's quickly look at a couple of other available statistics. Highlighting the total messages emitted shows a large volume of messages emanating from the IMU stream because of its high sample rate relative to the image frame rate. However, by highlighting the average message size, we can now see that the color, depth, and infrared image streams produce by far the largest messages. Note that message sizes are not collected by default and must be configured when enabling the diagnostics collection. This is because of the extra performance cost to serialize each message in order to determine its size in bytes. Recall, however, that we configured diagnostics earlier with the track message size option set to true, so we can now see the message size information here. There's much more information on this and more in the wiki. The ability to quickly see such statistics across the whole graph is extremely useful when diagnosing a SAI system. As you can imagine, this type of tool can be quite useful in identifying all sorts of problems in your applications. So hopefully this has given you at least a quick high-level view of the diagnostics collection and visualization capabilities in SAI Studio. Next, We'll see how we can use this to diagnose problems in our pipeline and components. Before we move on, we'll take a quick break to see if there are any questions.
Okay, so that was a quick high-level overview of this diagnostics visualization tool. I'm sure that was a lot of information to absorb there, and I know some of you might have already been using this tool, and to some of you, to others, this is probably just all new information. But nevertheless, we wanted to take a quick break here, just to see if there are any questions that we could answer live at this point in time. And we do have one question coming in now. So the question is, what is the expected impact of performance if the message size setting is enabled? Yeah, so basically what happens is by default, we don't have that setting enabled, because in order to calculate, or in order to determine the message size, we basically, for every message that's flowing through the entire pipeline, we have to essentially serialize the message to count the bytes. So as you can imagine, there will be some performance impact there. I mean, to sort of the extent of, like exactly how much performance impact that really is dependent, on the rate of messages, the size of messages and so on. But nevertheless, it's not something we have on by default, because in general, you generally just kind of want to have sort of more of the sort of overall some of the other statistics, such as sort of queue sizes, just to determine how messages are flowing. But then you can enable this one, but just know that it comes with some performance impact. Another question: can the tool be used both online and offline? Yes, it can. And yes, if used online, so basically what happens, if you're familiar with sort of other sort of, more traditional profiling tools like CPU profiling, basically when we enable it, it essentially runs a sort of mechanism in the background to sample all these statistics. Now we can control the sampling rate via configuration properties that I didn't show here, but there's definitely instructions on how to do that in the wiki page that I sent a link to. So yes, I mean, you can certainly tune that, but it will have some minimal performance impact in live mode. And I think I'll take one more questions, and then we'll go back, and feel free to continue posting more questions in the chat, of course. So this question from Willie says, in the general case, what is the performance impact for enabling diagnostics? Yeah, I think I sort of covered that. It is really dependent, again, on sort of rate of messages and how you tune that. So it's not enabled by default, because by default we don't want anyone experience any more impact on performance than they need to. So it's something that you have to explicitly go and enable. But yes, you can very quickly enable that, as I've shown, just by essentially just setting a flag, and then via configuration properties, you can tune. If you do start to experience some performance impact, you can fine tune, things like the sampling rate and so on. So with that, I think we should go back to the second part of the session, and then, like I said, keep your questions coming in, and we'll have time for Q&A right at the end as well.
Now let's take a look at two example problems in the remaining time. The first of these is an example of temporal synchronization using the join operator. One problem that arises sometimes when authoring Psi pipelines is that you'll write the code only to discover that no messages appear in some stream. This may happen when you fuse multiple streams, but do not correctly specify how the stream fusion should be done. We'll take a look at how diagnostics tools can help you quickly locate the source of the problem. But before that, though, let's do a quick review of data fusion and the join operator in Psi. One pattern that is often used in Psi pipelines is that of data fusion, where you have two different streams originating from different sources that need to be fused together. For example, here we have data coming in from a microphone and camera that eventually needs to be processed jointly by some audio-visual pipeline, and the data from these two streams needs to be synchronized first. Recall that each message is timestamped when it is first acquired, with an originating time that automatically flows with the message as it flows through the pipeline. This provides for latency awareness, so this component that needs to fuse the data here can pair the messages in the right way, based on when the original data was acquired in the world, rather than when the messages arrived at the component in wall clock time, as their latencies could be very different. This type of fusion is typically accomplished in Psi using the join stream operator. This operator takes as input a primary and a secondary stream, denoted here by P and S. Its job is to pair the messages arriving on these streams according to their originating times rather than their arrival times, creating message tuples as output. In the simplest case, this pairing is done by matching messages with identical originating times to create the output message tuples. However, the incoming messages on the two streams may not always align in originating times, so the join operator can be parameterized in different ways to specify how synchronization should be accomplished. What this boils down to is an interpolator, which, for each message received on the primary stream, determines which message it should be matched with on the secondary stream. Predefined interpolators are available for the most commonly used behaviors. For instance, here is an interpolator that selects the closest message in originating time to the primary message. In this case, message A would be matched with X, B would be matched with Y, and so would C. Then D and E would both get matched with Z. Alternatively, you could also specify an interpolator that only picks the nearest message within a configurable time window relative to the primary message, for example, from 50 milliseconds before to 10 milliseconds after. In this case, C would be matched with Y here, but no output would be generated for D, since there is no secondary message within that relative time window with respect to D. You could even have an interpolator that, instead of simply selecting secondary messages to match, actually computes a function over secondary values. A linear interpolator would be one such example. In summary, Psi provides a powerful set of built-in features that allow you to easily customize data fusion in many different ways. You can read more about this topic in the Stream Fusion and Merging page in the wiki. What this also means, however, is that if you configure things incorrectly, you may well see unexpected behavior in your Psi application. And that's a good segue back into how the diagnostics tools in Psi can help you identify such problems. Now recall that in the sample code, we joined the Resize color image stream with the depth image. The output of this is a tuple of the two synchronized messages. Let's also now add an inline write operator to this stream here, so that we can examine it later in Psi Studio. Remember that write lets you quickly save any stream to a store. In the second join, we fuse that output with the IMU stream. We'll also write the IMU stream to the store. Notice also that when we join with the IMU stream, we provided a time window here with this time span. This is just a shorthand way of specifying a time window interpolator for the join, as we saw earlier. Now imagine for a moment if we weren't careful to include this when we wrote the original join code, and just used instead the default join with no parameters. So let's try running it this way and see what happens. So what we would have expected to see would be the same ASCII rendition of the camera image, except now we don't see anything in the console window. So let's see how we can diagnose this problem in Psi Studio. Now if we select the total message emitted count in the diagnostics graph, we can see that the processor at the end of the pipeline, which draws to the console window, is receiving no messages. We can see this from the constant 0 value on the input to the processor. Working back up the graph, we can see that in this second join here, when we try to join the color and depth stream with the IMU stream, we don't get anything out. So let's look more closely at their messages. We can get a different view into the problem by visualizing the messages on each of the input streams to the join, which we wrote to the store earlier. We can right-click on the stream and select Visualize Messages. Each dot on the timeline represents a message on the stream at its originating time. We can zoom in on the stream to see the individual messages more clearly, and we can make the cursor snap to the exact message positions in the timeline by right-clicking and selecting Snap to Stream. Now let's plot the messages on the IMU stream right below. Note that the IMU messages do not align exactly with the color and depth messages. This is because the IMU operates on a different cadence to the image streams. Because we didn't use an interpolator with a tolerance window when joining these two streams, the join operator by default will only look for messages with perfectly aligned originating times, and we end up with no matching paired messages coming out of the join. As you can see, the Visualize Messages stream command can be very useful for debugging by allowing us to see when exactly in originating time things are happening at the individual stream level. While the diagnostics visualization helped us locate the source of the problem, which was upstream from the do operator that writes to the console, the Visualize Messages command helped us figure out what was going on. So now let's go back and check our code one more time. And sure enough, it turns out that we are using the default join, which is too restrictive in this case. We can fix this by modifying the join, adding back a timespan interpolation window within which to look for secondary messages to join with. And now, when we run the code again, hopefully the join will succeed this time and produce output messages. And indeed, we can see the console output image again, implying that the join is now working properly and messages are flowing all the way to the end of the pipeline once more. This brings us to the end of the first example. Alright, so now let's look at the second example problem. This is another one that you might sometimes encounter in your applications. Basically, you may at times observe that messages coming out of a component in your app appear to lag further and further behind with respect to originating time. This can happen if, for instance, you have a component that is slow and cannot keep up with the rate of incoming messages. Psi enables the application writer to control the flow of messages to help the application degrade gracefully when computational resources are insufficient to process messages as fast as they arrive. Let's briefly review how message delivery works in Psi, and in the process introduce the concept of delivery policies. In order to facilitate asynchronous delivery of messages between two connected components, each component receiver in Psi has a delivery queue. When a component generates a new message and posts it to its emitter, denoted by E here, that message gets added to the receiver's delivery queue. Eventually, the runtime scheduler picks up this message from the delivery queue and calls the receiver function to process it. As more messages are emitted, this process is repeated and messages continue to be processed so long as the receiving component is not too slow and can finish processing a message before the next one arrives. If, however, the component is slow, new messages will by default be queued upon arrival. This means that over time, more and more messages will queue up waiting to be processed. Given enough time, the component will eventually process them all, but the results will be produced at larger and larger delays with respect to the originating times of the incoming messages, as each successive message spends an ever-increasing amount of time in the queue waiting to be picked up by the receiver. Now, Psi allows application writers to regulate the message flow by specifying what is known as a delivery policy when creating the connection between emitter and receiver. This policy determines the queue size and behavior, and lets the application writer specify, among other things, how the connection should behave when messages are posted to the receiver at a different cadence from the receiving component. If you simply pipe an emitter to a receiver without specifying any delivery policy, this generally amounts to using an unlimited delivery policy, where the queue is allowed to grow indefinitely as messages arrive and await processing. While this ensures lossless delivery of messages, if the receiving component is not able to keep up, its output will become increasingly delayed with respect to originating times. In contrast, with a latest message delivery policy, whenever a new message arrives, it replaces any previous message already in the queue awaiting processing, and the older message is dropped. So long as the component is able to keep up with the rate of message arrival, all messages will be delivered and processed. However, if the component cannot keep up, then some messages will get dropped, and the component will always process the most recent or latest message. As with the join operator that we saw earlier, there's much more documentation in the Delivery Policies wiki page, where you can read more about other types of delivery policies, such as latency-constrained delivery policies, throttling policies, and so on. For now, though, let's return to our sample to see how the diagnostics visualization can help us diagnose problems related to delivery policies. Suppose now that I replace the resize operator here with a much slower component called slow resize. This slow resize component does essentially the same thing as the original resize component, but it simulates an additional processing delay with this sleep statement here. Let's also write the output of the slow resize component to the store. Now I'm going to run this pipeline again, and this time I notice that my output image frames appear to be slowed down as they lag further and further behind in real time as I move around. In addition, I also see that my application's memory usage grows steadily over time. So that's not good. Let's turn again to diagnostics to see how we can diagnose the problem. If we display the heat map of the average message emitted latencies, we can quickly see from the edges colored in red that this component here, which processes the color image, is the most likely culprit, introducing the latency which then carries forward to the downstream components, resulting in the delays that we observed in the rendered output. As we move forward in time, notice that the latency values just keep getting larger and larger. We can also examine the average delivery queue sizes to see that the color image messages are backing up in the delivery queue, waiting to be resized, causing the resized output images to lag further and further behind their originating times. This also explains the increasing memory consumption we observed, as all these large image messages accumulate in the queue. If we click on Show Delivery Policies, we can see that the unlimited delivery policy is being applied here, allowing the queue to grow indefinitely at the input to the slow component. As was shown in the previous session on data visualization with Psi Studio, another way to see the introduced latencies is to use the latency visualizer to plot message latencies on any stream. Remember, we saved the resized image stream So let's right-click on it and select Visualize Latency. And this brings up a latency plot, which is a visual representation of the latencies of messages on this stream. So each of these orange bars here represents a message. The bottom of the bar aligns in time with the message's originating time, and the top part of the bar shows the time at which the message was actually produced. In this case, the time when the slow resize component finished resizing the corresponding input image. So we can see here that as time goes on, each successive image is resized later and later with respect to its originating time, as messages are spending more and more time sitting in the delivery queue waiting to be processed. Also, here's another useful tip. Remember that we can click on any edge in the graph to bring up various statistics in a panel. If you right-click on the edge, this brings up a context menu which lets you add all these statistics to the session. Each one of these statistics may be visualized just like any other regular Psi stream. For instance, here's the message latency again, visualized as a numeric plot. This provides yet another way to examine the diagnostics information. Now that we have some idea of the root cause of the problem, let's actually go and fix our code. Because the slow resize component is inherently slow, we can change the delivery policy on its input to latest message to allow incoming messages to drop and enable the application to keep up. And indeed, when we run it now, we can see that the application is able to at least keep up in real time, albeit at a slower frame rate, since we are now allowing it to drop messages to compensate for the slow resize component. Finally, just to cap this all off, we can take a quick look again at the diagnostics graph to confirm that we are no longer introducing increasing latencies across the application. Instead, the latencies are now more or less steady throughout and reflect the processing time of the slow resize component, approximately 500 milliseconds. We can also visualize the message latencies of the resized image stream to see what they look like now. And as expected, the messages are being emitted with a more or less constant latency. Okay, so this brings us to the end of the debugging and diagnostics session. I know there was quite a lot covered here, so let's recap. We talked about how to enable diagnostics and use the diagnostics visualization in Psi Studio. We also covered some core constructs in Psi related to synchronization and controlling message flow using delivery policies. Then we looked at some techniques for diagnosing and debugging related issues. As always, you can revisit the tutorials we have on these topics and more in the various pages of the Psi Wiki. And finally, please let us know if you have any suggestions on how we might improve these tools to make debugging and diagnostics even easier in Psi. And with that, let's move on to questions.
Okay, well, I hope that was helpful. So that basically gave you an overview and a couple of examples of how you might enable and use the diagnostics feature in Psi to help give you more insight to your Psi applications and help you potentially debug them. I just want to take one question that came in during the second half of the session. The question was, can the diagnostic messages be inspected outside of Psi Studio? So yes, the diagnostics sampler, as you saw when diagnostics is enabled, basically enables this sampling mechanism that samples, at a regular configurable cadence, all the information from which these statistics, that we saw in the visualizer are computed. So some of these are derived statistics computed over a sort of average time window. Some of them are sort of statistics computed at points in time, basically at every sort of sampling, at every sample. So all of that information is then published as a regular Sci stream by this diagnostic sampler component. So you can certainly, as we saw, I think, as we showed in the first example, when we enable diagnostics, on the pipeline object, you basically have a diagnostics property, which represents that stream, that Sci stream, containing this sort of aggregate diagnostics object. So yes, you can get to it outside of SciStudio, except that it contains basically all the aggregate sampled information. So SciStudio does a little bit of magic, obviously, in its diagnostics visualizer to, basically extract out from this diagnostics stream, sort of the individual statistics that represent, sort of each connection and each node in the graph. And so that information is all, sort of contained in aggregate on this diagnostic stream. So yes, it's it's certainly accessible, but you have to do some additional computation. We haven't sort of gotten down to the level, I think, of, sort of enabling, one to just, easily extract that out. But, for that, we have the visualization tool in SciStudio to do that. So let's see, we've got I think another question. So yes, in debugging, why a join is not yielding any messages. Do you have any suggestions on how to identify the right interpolator to resolve the issue? Is this mostly looking at the message latencies? That's a good question. Yeah, so obviously with the interpolators, like there's a whole range of interpolators. I mean, typically when you don't get any messages out, that's kind of, and that's sort of based on, I guess, sort of our experience, sort of writing a lot of these kinds of applications, is that typically when that happens, either you're not getting messages in, right? Or somehow, you're not getting messages in on one of the streams, and so things are just queued up waiting to find a message. But in the example that I showed, we could clearly see that messages were coming in to, sort of both inputs to the join. So that's when you kind of suspect that, well, there's something in the interpolator, and probably, most likely is the case that we're either, sort of the interpolator that we're using is too restrictive. Either it's a exact interpolator, right, where it's looking for an exact matching message, or even if we specify a tolerance window, maybe that window is too small. So that kind of clues you in, I guess, at least to start kind of examining in sort of finer grained detail, by sort of looking at the individual messages, looking at the latencies, and then figuring it out from there. So yeah, it's really just kind of based more on that sort of, sort of learned heuristic, I guess. Right. Well, I don't see any more messages or more questions coming in at this point. So perhaps I could just wrap up with a couple of comments. Like, I hope you guys who have already been using it, thank you for the feedback. Keep the feedback coming in. As I said, we wrote this feature basically, sort of motivated by our need to debug our applications. But it'd be great to have, sort of, diverse perspectives and sort of, get views from other people who have used it. And if you haven't tried it yet, by all means, please, have a look at it, have a go, and then, as always, give us feedback, via our GitHub issues page. Yeah, so I think it's almost 9:50. So with that, I think I'm going to wrap up here. And next up, my colleague Ashley is going to present some really cool features on how to interoperate between Sci and Python, as well as Sci and Rust. So stay tuned. Thank you.
Hey everyone, my name's Ashley Finello. I'm one of the engineers on the Psi team. We're going to spend about the next 25 minutes learning about how Psi interoperates with Python and potentially other languages, and do a coding session from scratch demonstrating this capability. When we say interoperation between Psi and other languages, we really mean communication across processes. Psi in one process conveying message streams to and from another process that's not running Psi. The coding session will be fairly simple, but the mechanics around shuttling messages back and forth and around maintaining originating times on messages will apply equally well to arbitrarily complex systems. We'll be using ZeroMQ, which is a widely supported messaging infrastructure across many different languages. In .NET, it's called NetMQ, so we'll use the NetMQ writer and source components, which are available in the Microsoft.Psi.interop namespace. Also in that namespace are format serializers for message pack, which is a nice binary format, JSON, which is a nice text format, CSV. You can extend this with your own formats. You can extend it with your own transports. In the particular sample that we'll be building, we will use a media capture component to capture video and send that over ZeroMQ to the Python side. We'll use message pack. So on the Python side, we'll use a ZeroMQ and message pack library that's already available to receive those messages, and we'll use OpenCV to detect faces in the frames of video. Then we'll send back bounding rectangles of those detected faces back to Psi. And throughout this whole process, we'll maintain the originating time from the media capture component through the Python world and back into the Psi world. That way we can do accurate cropping at the end. And along the way, we'll store all of this in a Psi store, and we'll look at it in Platform for Situated Intelligence Studio, Psi Studio. So we'll learn about the tools, we'll learn about some of the infrastructure, and this cross-process communication infrastructure that's available with Psi. I should point out that if you're actually just trying to communicate between two Psi processes, then we should use something else called just remoting. So we have remote importers and remote exporters that will shuttle Psi messages over TCP, UDP, or named pipes, and will maintain the fidelity of the .NET types as they go over the wire, and we'll use the super efficient serialization mechanisms already built into Psi. Also supports back pressure and intermittent and late connections with replay, a bunch of interesting features. So that's what you really should use to communicate between Psi processes. But if it's Psi on one end and, say, Python on the other, or Node.js, JavaScript on the other, or something else, that's when you'd use the components available in the Microsoft.Psi.interop library, and that's what we'll be talking about today. We're going to be going through the sample pretty quickly, but if you want to follow along later, perhaps, we can go to the GitHub, click here for the wiki, and then scroll down on the right bar. There's a section, Bridging to Other Ecosystems and Bridging to Python. Also above here, by the way, is a doc on remoting that we just talked about. So this is the sample we're going to go through, this Python interop walkthrough. So let's just get started. We'll use the .NET command line tool to create a new console app. Let's call it Face Detection, and this will be a framework app instead of a .NET Core app because of one of the dependencies. So this will create the project, and then we'll just go into that directory, and next we'll add some NuGet packages. So if we go back to the wiki, you can see that on the sidebar here, there's a link to a list of available NuGet packages in Psi. And looking at that list, you can see that for each of the packages, it lists whether it's available for Linux, for Windows, or perhaps both. And in general, anything that ends with no suffix is available for both. So here audio, and this works on both. Or here's some particular pieces that work only on Linux, or pieces that work only on Windows. And so here's one that we actually will be using. We'll need Psi imaging. So there's bits of that work on any platform, and there's some that work only on Linux or Windows. In particular, this sample will build it for Windows, but if you look in the wiki at the Python walkthrough, there are instructions also to get it working on Linux. And it's really just a couple of lines of code that change. Here's an example, though, of a package, the Windows x64. This actually doesn't target any CPU. This targets x64, so we'll get into that in a moment also. So first, I know we're going to need the Microsoft.Psi.imaging package. And like we said, that's available for Linux or Windows. We're going to be using some of the encoders, so we'll need the Windows version of that. And these are pre-release, so we'll need to set that flag. Next, we're going to need the media library, which contains the media capture component that we'll use to capture video. And this one happens to be x64 specific. So finally, we're going to need the interop library, which will allow us to talk over 0MQ and encode the message pack. So while we're at it, let's just do the same for Python. Install the 0MQ library, the message pack library. OpenCV we'll use for face detection, and Pillow is the Python imaging library. Having libraries like this 0MQ and message pack available in a plethora of languages is why we chose these for our interop story. Now, just to kind of get all of our projects set up before we really get started, let's create the Python side, so facedetection.py. And we'll just import the libraries that we've installed, 0MQ, Message Pack, OpenCV, and some others that we'll need. So we'll use VS Code for editing the Python side, and we'll use Visual Studio for working on the .NET side. So the CS proj for Visual Studio has already been created. And one thing we do need to do is make sure that this project is set for x64 because of one of our dependencies. And we're good to go. So to kick things off, let's start on the Psi side of things. Use the media capture component to capture video. We'll store it in the Psi store and take a look at it in Psi Studio. So first we'll include the namespaces that we need. Of course, Psi itself for the runtime. And we'll also need imaging and media. And of course, interop. And now interop is broken into two pieces. So there's the formats, which include things like JSON and message pack, and there's transports for things like 0MQ. So any Psi application begins with creating a Psi pipeline, and everything runs within that pipeline, and disposing of that pipeline stops it. So we use a using here, create the pipeline, and everything inside the using represents constructing the components inside the pipeline. So you can either run the pipeline, just a blocking run that will exit when all of the components have completed, or since the media capture component really is an infinite source, we'll run it async and we'll just wait for the user to hit enter, falling out of the using, disposing and stopping the pipeline. So creating the media capture component is just a class, but it takes a pipeline in its constructor. Most Psi components do. They use that to create their emitters and receivers. And it takes some configuration information, the width and height of the video. And in this case, I'm using a Surface Book and I have to specify to use the front camera. It defaults to the back camera otherwise. Device IDs like these are listed in the Device Manager in Windows. Or in Linux, you can just ls your dev directory. And you should see things like video 0, video 1, etc. Then we want to write that to a Psi store. So creating a Psi store is a similar pattern to creating a pipeline. It's Psi store.create. And it takes a pipeline as one of its arguments, along with a name and a path to where to store it on disk. And at that location, it will store a bunch of data extents, a catalog of all of the streams, an index. We can then write the main output stream of this capture component to the store. And this can be done quite simply with this capture.write, giving it a name and a store to write to. Alright, so now let's just try running this. That doesn't show much, but I can see that my camera's on. And if we switch to Psi Studio, we should be able to open up the data store that it's saving. So here you go. We have this catalog, we have an index, and then these data extents keep being added. 1/4 gigs each, so it's quite a bit of data being collected very quickly. But we can open this up, and inside Studio we can see that we're live, and we have this one capture stream, which is a shared image. So let's take a look at it. And there we go. Just wanted to check that the app is working. We can go back here, stop this. And then now inside Studio, it's no longer live, but we can scrub through the data. So next, let's use the NetMQ Writer component from Microsoft Psi Interop to write this over 0MQ message queue using message pack over TCP. The netMQ writer is the component that we'll use to communicate over 0MQ. What we plan to do is encode our video frames as JPEG, and so we'll send them over as byte arrays. So we specify that in the type parameters. Then the component takes a pipeline, like most components, and it also takes a topic name and an address. So that's how 0MQ works. You can send multiple topics over a given port and distinguish them that way. We'll use the topic name frames and arbitrarily port 30,000 on the loopback address. And we'll use message pack format for serialization. Now this is going to be a taste of what it really looks like to program in Psi. It looks a lot like Link with stream operators. Here we'll take the capture stream and encode it as JPEGs, 90% quality, and delivery policy that says to take the latest message if the encoder can't keep up. Delivery policies were covered in a bit more detail in the previous session by Nick, but essentially this tells the pipeline here that if messages begin to queue in front of the encoder, because they're being delivered faster than they can be encoded, then just encode the latest message and drop older messages. This ensures that the pipeline doesn't fall behind. From that, we'll select out just the byte array buffer. And just so that we don't overload the Python side in this little sample, we'll just sample this stream down to 5 Hertz. Then finally, we'll pipe the output to the writer, and that's what will be written over 0MQ. So we'll just run this, we'll leave it running while we switch over to the Python side, where we'll use 0MQ to receive the messages and OpenCV now to detect faces. So to receive input over 0MQ in Python, we will open up a socket and specify that we want to be a subscriber. So socket's going to have multiple topics per socket. Here we'll set an option that filters to just the frames topic that we specified on the Psi side of things. Then we'll also connect now to the address that we're publishing to from the Psi side of things, including this port 30,000 that we chose arbitrarily. So now we'll just read the frames one at a time off the queue, and what we get is this multi-part tuple containing a topic and the payload. You can use that topic to do filtering in code, but we know that we're just going to be receiving the one topic. You can unpack the message using message pack quite simply, and the message that we get from Psi will always contain these two fields, a message field that contains the actual payload, and an originating time field that contains the time that this data originated in the real world, so at the media capture component in the Psi world. The data is just this byte array, which we'll read in, we'll unpack it as a proper Python image, and then we'll convert that to a NumPy array because we're going to be using OpenCV in a moment. And notice that we return the image and the originating time. We're going to have to keep track of that originating time. So for face detection, we're just going to use these cascade classifiers in OpenCV. If we go back to the walkthrough on the wiki, look at where it's talking about these, there's a link to the OpenCV repository where we can find these classifiers. Now there's actually a bunch of them. There's classifiers for eye detection, for profile faces. The one that we're going to use though is just this frontal face classifier. So we'll need to download that, save it into our project. It's just an XML file describing the model. And then we'll need to reference that in code here. So face detection itself is extremely simple. This is really the core of what we're doing here. The rest is kind of plumbing, just to get data in and back out. But literally to detect faces, we just detect multiscale on a frame, which is a NumPy array from an image that's been sent over. So we can sit in a while loop, just reading in frames and running them through the detector. And what you get out is a list of rectangles, of the bounding rectangles around faces that have been detected. So we can just loop through each of those, and let's just print, let's say, the X and Y properties, just so we can see, I can move my head and we can see that those values are changing. This should be pretty simple to do. And then we can just run this, and remember the Psi side is still running, pumping images, and here we go. Python receives them and detects faces. I can move my head, you can see the X and Y's are moving. Seems to work great. All right, so let's go the other way around and take the detected face rectangles and send them back to Psi over 0MQ. So output is very similar to input, but instead of a subscription socket, we'll use a pub socket, and we'll use a new port number, 30001, bind to that. So now to write the faces, we're going to, of course, need the faces themselves, and we're going to need that originating time back, because we need to be able to correlate everything. So we get this set of rectangles, and I want to convert these, though, to a face object type. So the faces that come back are NumPy data structures, and those don't translate very well over message pack. So for each of the faces that come in, we're just going to create a new face structure. It's just going to be a simple object with just an XY width height property. And it's a good idea to use the most primitive types possible. So convert from those NumPy integers to just regular Python integers. And this will translate much better over the wire. So then just append those to the rects array, and we'll build up an array of these faces that we've detected. If we have detected any, so we won't bother sending empty rectangle arrays. That actually might be useful information in itself, but just to save some traffic, we won't send those. The payload that we want to construct looks like the same kind of payload that you get over the wire from Psi. So they always have this message field, and that'll contain your payload. It can be anything. Here it's this list of rectangles, and an originating time. And here we'll just pass the same originating time back through. So that can all be correlated. These messages coming back from Python have the same originating time as the original media capture messages coming in. And so then you just send that over 0MQ. We use a new topic name. We'll just call it faces. It has to be UTF-8 encoded. And then just use message pack to encode the data. And so that's what the Psi side will expect. And so that's it. There's our write faces function. We can just add that to the while loop. And so we're reading frames and detecting faces and then writing those faces back out, threading the originating time through. So let's go back to the Psi side now and consume this stream of face rectangles. So here we'll use the netmq source component to read the socket. It's going to be a stream of dynamics because this is coming from the Python world, and so it's not a .NET type. We'll need to convert that. This component takes the topic name, faces, and the new address that we were publishing on from the Python side, port 30001. We'll use message pack again to deserialize it because that's what we used on the Python side to serialize it. So face source is a stream of dynamics now. Each of those we know is actually a list of face rectangles, but we'll need to do a select over them to convert them. So we'll need a couple of namespaces. We'll need link for one. We'll need generic collections, and we're going to need system drawing for the rectangle class. So it's interesting. The outer select here is a select on a stream, and that's a Psi stream operator. But here we're going to do a select over this IEnumerable of dynamics. To get IntelliSense to work, we'll cast it here. So this is a select over just the rectangle list, and for each of the rectangles we want to convert it to a system drawing rectangle. So we'll just create a new one of those and pull out the properties from this, what comes over as a dictionary. The object in Python world just became a dictionary on this end when MessagePack deserialized it. Now interestingly, we can't just return this IEnumerable of system drawing rectangles. The quick explanation is that it's not a concrete type. Under the covers, it's a suspended continuation, and it's not safe for Psi to clone that. So we'll convert it to a concrete list, and then we can write that to the store and visualize it in Psi Studio. All right, so let's try running this again. So the Python side is still running. I see my camera come up, so we should be able to go to Psi Studio. And here you can see we're not live, but we can open up the most recent data store, which will be this one. And there we are, we're live again. So we have a new stream type, faces, which is a stream of lists of rectangles. We can visualize that. And there we are. Let's make it a little thicker. There we go, face tracking in action. So, of course, the reason it's a list of rectangles is it should work on multiple faces. No problem. So this is not too bad. The one thing that I might worry about, though, is this latency. So, can completely outrun the crop area there. And this is an area that Psi is very good at, so let's learn about that next. So what we want to do is now take our sets of rectangles and our sets of images from media capture and produce a new stream now of cropped images using those face rectangles. We'll just take the nearest face and crop that. So to determine what is the nearest face, we'll just use the size of the face rectangle. So the faces stream is a stream of lists of rectangles, remember. And so we'll do a select over that, and that's a stream operator, a Psi stream operator. Within, though, for each list of face rectangles, we'll use a link expression, order them by their size, which we'll determine by just the width times height of the individual rectangles. And then we'll just take the first of those. So it's interesting, we have link expressions contained within Psi link-like expressions. So what we want now is to use the two streams that we have, the original image stream from media capture and this new stream of face rectangles, and combine them and create a new stream that's tuples of rectangles and images that go together. And we already have in the image library a crop operation that works on such streams to perform the crop itself, so that's easy. But how exactly to combine these streams is a little more difficult. So the image stream is pretty dense and it's a nice consistent interval. The face rectangles, though, because of the network latency and other things, come in much more sparsely and much less consistently. So if we use the pair operation shown here, then we get a nice dense stream out. For each image that came in, there's a tuple going out. But what's happening is that each image is being paired with the last known rectangle on the faces stream. And those rectangles may be out of date. The face may have moved or been occluded since then. So another operation we can try is join. And so join, instead of just blindly pairing with the last known rectangle, instead it'll try to find a rectangle that's the highest quality match, given some criteria, and it's highly configurable. But for example, you could give it a small window, and if it doesn't find a match within that window, then it will just drop the image. So you can see on the output stream here, some of the images have been dropped because a match just couldn't be found that matches the criteria. The window that you provide could be backward-looking. It could also be forward-looking. So, for example, the fourth one over here is actually matching with a rectangle from the future. So, joins definitely introduce a latency to the system, waiting for these messages from the future, for example. And actually, if you think about it, all of this is happening in originating time rather than wall clock time. So, even when it finds a match, to be able to prove that that's the best match, it needs to see the next message also and see its originating time. Because it's not about when it arrives in wall clock time, but what is the originating time on that message when it arrives. So a join definitely introduces latency to the system necessarily, but it creates a higher quality set of matches. And we'll compare the two. So we'll take our capture stream, which is our stream of images from media capture, and pair that with the nearest faces stream, which is a stream of single rectangles of the nearest face, producing a stream of tuples of images and rectangles, and the crop operator takes that. So just like that, we get a stream of cropped images. And we'll write those to the store so that we can look at it in Psi Studio and see if we can see the latency differences or the quality of the match differences. So we'll do exactly the same thing, but this time for join, and we'll just write it to another stream in the store, call it with join instead of with pair, so we can distinguish them. And for join, we'll give it a small time window of 100 milliseconds. So we get pretty good quality matches. All right, so let's run this again. Python site is still running. And my camera comes on. We can switch over to Psi Studio and open up the latest store. This one. And there we go, we're live again. And let me remove this panel. And let's take a look at what the cropped with pair versus the cropped with join looks like. So, let's see. So you can see the one on the right is keeping up quite well. So let's see if I can really outrun this and really show the latency. If I make sudden movements, or if my face is lost for a while, what happens? So let's stop producing data here. Now, scrubbing through the data, let's see if we can find some good examples of pair versus join. So like, for example, right here, you can see pair continues to crop even in occluded and moved face, and it's just using outdated rectangles to do that. Meanwhile, join instead just doesn't produce data. Or here, let's find another. Here's a good one. So, of course, the face is moved, pair continues to crop, just a blank background. And join, we gave it a 100 millisecond window, so it's not perfect, but it's much, much better. So this shows the importance of threading the originating time through the Python world and back to the Psi world, where we can make choices about the compromises that we want to make when fusing these streams. So we can choose a low latency dense stream, or we can trade some density and some latency for higher quality. This is the kind of thing that you can do with Psi. So hopefully you found this session fun, and we learned something about using Microsoft.Psi.interop to interoperate with other ecosystems, and how to use Psi Studio to visualize things as we go, and even to debug latency and quality issues. And then, of course, the importance of originating times and the power of the join algebra in Psi. So let's move on to the Q&A session. All right, so that was pretty fun. Thanks for attending this, and I want to remind people to go ahead and post questions in the chat, and we'll try to get to those during this time, and if we don't, we'll get to them in the chat later. Let's see what we do have. So I do see one question, at least from Shirag, asking, just to confirm, the pub-sub pattern in the presentation, is it for just illustration, and are there no API restrictions that exist on the socket patterns for the topology on the Psi side? So honestly, the NetMQ readers and writers, they actually do open publisher and subscriber sockets on the Psi side, and that's hard coded in the code. That's something that'd be very easy to make configurable. That's something maybe I'll open a work item to do, actually. Some of those patterns, though, may not be a good fit for Psi, or may be complicated to integrate with Psi. For example, the request response pattern. We don't actually have that kind of thing in Psi. You could build such a thing as a protocol, maybe with a pair of streams, sending a request with an ID on one stream and a response with a corresponding ID on another. But we'd have to think actually about how to integrate with some of the other highly configurable things that you can do with ZeroMQ. For the moment, the components that are in there, they just really are a pub and a sub socket. Let's see. Hopefully that answers that. And actually, Shirag, we would love to talk to you more and hear some of your usage patterns, for doing this kind of thing, and see, real world examples of what people would be using it for, and we'll extend things as we need to. Be sure to answer or send more questions in the chat, but I'll go ahead and go to some questions that I know people have asked in the past. And actually, it's one thing that we didn't cover in this presentation, which is basically how do you consume Psi stores directly in Python or some other language without having to run a live Psi system on one end. Maybe you're just doing offline training in Python and you just want to feed a bunch of data in. Maybe you've collected the data with Psi, but you just want to run it offline or do some analysis over a Psi store. So of course you can imagine after seeing this presentation that it would just take a couple of lines of code really to open up a Psi store, open up a stream, and send it over ZeroMQ to another language. But there actually is a command line tool checked in alongside Psi Studio in the tools directory. It's called Psi Store Tool. This command line lets you open up Psi stores, explore them, list what streams are in there, check out the metadata, even look at individual messages, and it has some operations built in for doing interesting things with stores like cropping them, merging them. And one of the operations is quite simply just send this stream over ZeroMQ using whatever format you would like. So you specify that, you specify an address, and it'll just open up that store and send it for you. So it becomes one line of bash to open up a Psi store and ship it over to another language. Another thing related is that these inside Microsoft.Psi.interop, there's also file readers and writers. So instead of sending it over ZeroMQ, you could just write it to a file. and it could be JSON or message pack or some ubiquitous format that you can just parse in their language as a flat file. You can also read files, flat files into Psi using that mechanism. Let's see if we have any other interesting questions. Not really, but I'll give people a little bit of time. We've got, another 10 minutes or so before the official break. We could break early, but maybe another question people ask is, what other languages does this work with? So of course the demo was in Python, and the name of the talk even is interoperating with Python, but the mechanics work in a huge number of languages. The ZeroMQ infrastructure is available in at least 15, 20 languages. I know C, C++, all of the .NET languages, F#, C#, managed C++, Python, Ruby, even some weird ones I know. Haskell, Erlang has ZeroMQ implementations. And then the file formats, obviously JSON is absolutely ubiquitous. I'm sure it's available in every single language. And message pack is available in something like 50 languages. So it covers the gamut of languages you might be using. Let's see if we have any other very good questions to look at. Really? So, I'll just remind people again, go ahead and put questions in the chat. Even after this, we'll go ahead and answer them in the chat. And so now we have a break coming up till 10:45. And at that point, I'll come back actually and do another talk on interoperating with ROS. So we'll learn how to build hybrid systems using ROS and Psi together. So have a nice break. Thanks for attending. Hi, everyone, and welcome back. I'm Ashley Finello, one of the engineers on the Psi team. In this session, we're going to talk about how Psi can interoperate with ROS, the robot operating system. So ROS is really the de facto standard for robotics work and has a huge community. Virtually any robotic hardware that you might have is certain to have a ROS package available for it. Psi also can be used to build multimodal integrative systems, but perhaps it has an ecosystem that's more centered around human interaction than low-level robot control. In this session, though, we'll talk about how we can bring the two together and leverage the best of both worlds. We'll start with a small crash course in ROS itself, and then we'll get into how ROS and Psi play well together. Then we'll look at a prototype hybrid system leveraging the complementary capabilities of both ROS and Psi. And finally, we'll spend about 15 minutes or so walking through a coding sample, communicating with the ROS turtle sim from Psi. So let's start off with a little crash course in ROS itself. So ROS is a lot like Psi in that it's also an actor model system with loosely coupled cohesive components communicating through message passing. Components in ROS are called nodes, and they are orchestrated by what's called the ROS master. So every ROS system, you run ROS core, it launches a process that hosts the ROS master. That same process hosts the parameter server, which is a central place for nodes to share configuration information. Unlike Psi, where piping the output from one component to the input of another is explicitly expressed in code, in ROS, nodes don't explicitly know about each other. Instead, they communicate through topics, which are just named channels. So nodes will go to the master and advertise that they intend to publish a particular topic and that they would like to subscribe to a particular topic. And the master will keep track of all of the nodes and tell nodes about each other. Tell the node on the left, let's say, that the node on the right has the topic that it wants. Then it's up to the nodes to negotiate peer-to-peer connections. So once peer-to-peer connections have been established, then the master is essentially out of the loop as far as message passing. That all just happens peer-to-peer over TCP or UDP connections between the nodes. So looking at this a little bit closer, you can see that ROS core would be one process, and each node would be individual processes. So this small graph would have 3 processes running, all communicating with each other through interprocess communications. XML RPC between the nodes and the master to orchestrate things. Message passing in particular is a binary format that's specified by ROS. So there's a set of primitives that you can use to compose messages, and there's a set of composite data types that you can use to create schemas. And regardless of what language you're using, so we show here using Python on the left and using C++ on the right, data structures in those languages would need to be translated into proper ROS messages to be transmitted over the wire. That's in contrast to Psi, where everything is in .NET and any .NET type is a valid message. Another area of flexibility in ROS is that nodes being separate processes and the communication being a protocol, nodes can be written in any language. So we show here the node on the left written in Python, the node on the right written in C++. They can communicate fine as long as they both understand the XML-RPC protocol and can serialize and deserialize messages in the proper ROS format. Another aspect of ROS that I wanted to point out is ROS bags, which is a file format for storing messages to flat files. There's a tool called ROS bag that you can ask to record messages in the system. It acts a lot like a node and goes out to the master to discover what publishers there are and subscribes to them so that it can collect their data to save it. You can ask it to collect a particular node, particular topic, the whole graph, anything you like. Then the idea is that you can remove nodes from the system and instead play them back from flat files. And because of this loose topic-based binding system, that's quite natural. ROSBag can play back a topic and other nodes in the system have no idea that it's coming from a file rather than a live node. Let's talk now about how ROS and Psi can talk to each other through what we call the ROS bridge. The fact that ROS is language agnostic is pretty important for what we're trying to do here. That's essentially what the ROS bridge is, this library that's available along with Psi in the Psi repo. It allows us to create ROS nodes using .NET languages, C# or F#. And these nodes can communicate with the ROS master, discover other nodes, negotiate peer-to-peer connections with those nodes, and serialize and deserialize messages. Then, of course, the idea is to create Psi components using these nodes, and then create Psi applications. So essentially a Psi graph is fused with a ROS graph, and you have a hybrid application. Here's a real-world example system using Psi and ROS together.
That's a short walk.
This is a prototype system that we built that would interact with people needing directions throughout our building. We would lead them to their destinations. So you can see that it navigates around static obstacles that are on the map quite easily. And you'll see in a second that it navigates around dynamic obstacles like Dan standing in the way here. The beauty is that we didn't have to build this navigation stack. This is just a ROS package. We got to focus on our research interests having to do with the human interaction components in Psi while leveraging ROS for the nav stack and the low-level robot control.
Arrived at 3,800.
Here's the architecture of the system. So the base was a Pioneer LX with a built-in computer running Linux, and that's where we ran ROS. Then we also had on board a Intel NUC running Windows, and that's where we ran Psi. And then of course we have the Now robot, and we have a bunch of other sensors. We have a couple of point gray cameras and a Kinect. So on the ROS side, we ran a ROS package to control the Now, and we ran a ROS package to do all of the indoor navigation and SLAM. Then on the Windows side, we of course had matching components on the Psi side to talk to ROS for the Now and the ARNL, and then a bunch of Psi components constructing a graph to do all of the human interaction. So face tracking from the point gray cameras, and we actually used the Kinect mostly for the mic array. And so we would do speech and send things up to the cloud for speech recognition and use Lewis for intent. And we had a whole controller finite state machine that would run the robot's dialogue system. This hybrid architecture is probably a pretty common way to run ROS and Psi. Running ROS on the Linux side, running Psi maybe on the Windows side. So this split architecture is what we chose, but you should remember that Psi actually runs on Linux also. And ROS also runs on Windows, so it's your choice. This is what we chose to do. To get a good, solid understanding of how all of this works, let's spend about the next 15 minutes going through one of the samples available in our samples repo. The TurtleSim sample is a good one to start with. Okay, so what we're going to do is build a little Psi application to talk to this TurtleSim running in ROS. So the TurtleSim node comes up, it notifies the ROS master that it wants to subscribe to a command velocity topic to control the turtle, and it wants to publish to a pose topic, updating its position. And so we'll create a turtle class just in .NET, and using the ROS bridge, we'll create a ROS node that essentially wants to do the inverse. It wants to publish to a command velocity topic and subscribe to a pose topic. So it goes out to the ROS master and tries to discover other nodes that have matching topics and close that gap, negotiating a peer-to-peer connection between the two. And being just plain .NET, this turtle class will just have a velocity method that you can call to give velocities, and that'll cause a command velocity message to be pushed out. And it will just have an onPoseChanged event, regular .NET event that will be fired when pose messages come in. So we're still just in plain .NET. We'll wrap that though then now with another class, which we'll call turtle component. That will be a proper Psi component. It'll turn that event and that method into proper Psi streams named velocity and pose. So velocity stream will be a receiver that pushes to that velocity method, and pose will be a stream to which messages will be pushed when the event fires underneath. This kind of separation of concerns of having a separate turtle class that knows about ROS and knows about how to control the turtle sim, but doesn't know about Psi, and then thinly wrapping that as a Psi component is a good general architecture. Then finally, we'll create an app that starts a Psi pipeline and uses this turtle component to allow us to drive the turtle around with the keyboard. So let's look a little bit closer at the ROS bridge itself, actually, before we get started. I just wanted to give a concrete view of the library that we'll be using to talk to ROS from .NET. This is in the Psi repo under Sources, Integrations, ROS, Microsoft.psi.ros. And it's also available as a NuGet package by the same name, Microsoft.psi.ros. And you see the files here are .fs files, that's F#. So this is a nice functional language in .NET. But don't worry, you don't have to learn that language to use it. We'll be using it from C#. So in the ROS bridge, there are classes for creating nodes, for creating publishers and subscribers, for creating clients to the parameter server, regular service clients, and then classes that know how to speak the protocol, to talk to the master and to talk to other nodes and serialize ROS messages. So serializing ROS messages, you need to be able to represent the message structure, and so that's what this is for. This is basically what ROS messages are made out of. And the reason that we really want to know about this in depth is that for non-standard ROS messages, we're going to need to create our own definitions out of this structure. And we'll get into that in the sample, but I just wanted to show right here in the bridge how it really works. So these are the primitives. They have Boolean types, integers of various sizes and signs, floating point values of 30 or 32 or 64-bit, date times and time spans, strings, and then composite types from these, variable and fixed length arrays of these primitive types, or structures that are essentially just a name value pair. And all of these can be nested, so you can create any shaped message structure that you like with these primitives. But at the leaves, it's all just these primitives only. So a message type definition really is a type name and an MD5 hash that is somewhat strongly typed, at least to make sure that nodes can agree that they're really talking about the same type, and a list of these field definitions. That's what makes up a message definition. Now, all of the standard message definitions that come with ROS, we have a bunch of those defined already coming with the ROS bridge. So there's like the standard header. One that we're going to use in this sample is the geometry twist message. So there it is. Just has this linear and angular fields that are each vector 3Ds, and whatever a vector 3D is defined elsewhere in here also. So that gives you at least some concrete idea of how the bridge works. Let's go ahead and start up ROS core, which will spin up the master, spin up the parameter server, and then let's spin up the turtle sim. And we'll just run these in the background and leave them running while we develop the sample. This is generally how we work with ROS. Just leave it up running and work on the .NET side. So using some of the ROS tools, we can now that that's running in the background, we can query for what topics are being published and that are available for subscription. So there's the command velocity topic that we know about, and the pose topic from the turtle. And there's this other color sensor topic, which we'll ignore for now. We can look a little bit deeper into these topics and see exactly what they are. So command velocity really is a geometry twist message, which we just looked at. So we actually know we already have a definition for that type. We can go ahead and look, though, at what exactly is a geometry twist, even though we just saw it in source code. This is what Ross says it is. It's a pair of vector 3Ds, or vector 3s, a linear and an angular. And each of the vector 3s are just 3 float 64s. So that's a pretty simple message format. It's actually kind of overspecified for this little 2D robot, though. And we'll see how that works out. If we want, we can look at the pose topic also and see what that's made of. And notice that is a message type that's not standard. TurtleSim/pose, that's something that the TurtleSim developers came up with themselves. It's just 5 float 32s, pretty simple. X, Y, theta, and I guess a linear and angular velocity, which I think we'll ignore. We'll just use the X, Y, theta. And again, you can dig in and see, what is the MD5 hash of that, which we'll actually need that later for making our own definition for this non-standard message format. So now let's go ahead and clone the sample repo. So this isn't going to be a code walkthrough where we build everything from scratch, starting with nothing. We're just going to take one of the existing samples and we'll walk through and see how it works in detail. So inside the sample repo, there's a couple of ROS samples. One is a UARM control, but you need actual hardware for that one. This is a fun example, though, of using ROS with the GNU-Go game engine and some rudimentary vision with OpenCV, all brought together in a Psi application that plays Go. ROS Turtle, though, is just a simulator, and it's a node that actually comes with ROS, so it's very easy to get started with. So again, that sample is going to contain this turtle class, like we said, that just knows how to talk to the turtle sim and knows about ROS. And then this turtle component wrapping that lives in the Psi world, turning those things into streams. And then a program that uses that component. So let's look at the turtle first. The turtle is just a simple .NET class. We're going to include the Microsoft ROS NuGet and this namespace so that we can use that. And we'll call our node just turtle sample, turtle_sample. And we know that we're going to deal with these two topics, so we need to have strings that match those names that we'll discover through the master. And then we also need to, of course, know where the master is, what's its address. And then we need a host name for ourselves as well. So we're going to end up creating a ROS node and holding on to it, and with that node creating a publisher and a subscriber. So remember that message type, the TurtleSim pose, was not a standard message type. And so we have to define its structure ourselves for the serializer to understand what to do with these messages. So its name was TurtleSim/pose. That's dictated by the TurtleSim guys. And its MD5 hash is also dictated by them. So we would have to have gotten this MD5 hash from the tooling. And so remember that was just ROS message MD5 and give the name of a message type and it'll give you the MD5 hash of it. So that's where that came from. Then the fields, we need to actually define those as well. X, Y, theta, and angular and linear velocity. And there are float 32s. How did we know that? Well, the tools give us that as well. So just, let's see, ROS message, just get info. And there you go, it's the 5 float 32s. So we have to define something that matches that. We have to write that ourselves because it's not a standard message type. So now when you create an instance of our turtle class, you're going to have to give us the host name, or the address of the master, and a host name to use for ourselves when talking to the master. We'll store those away. And then, we're going to have this pose changed event that we're going to fire whenever pose change messages come in. So we have that. And it's just a triple of floats. It's going to be the X, Y, theta. We'll ignore the velocities. And then when we're asked to connect, that's the point that we will create a ROS node. And that will actually connect to the master at that point. Then now from that node, we will create a publisher. And since this is a pre-built message type, we can just use it from the library, geometry twist definition. And for the subscriber, and we'll create that from the node as well, we'll use our custom message definition that we just made up above. And what happens when messages come in to the subscribers, it calls a callback and passes the message to it. So for that, we'll use this pose update method defined down below. We'll look at it in a moment. When we disconnect, we basically just do the opposite. We have to unregister the publisher and unregister the subscriber. And that just tells the ROS master that we've gone away, and it'll notify any other nodes. And the velocity method, we're just going to take linear and angular, and we'll have to plug it into this structure. That's the message that it's expecting, which is a geometry twist message that has 2 vector 3s. But it's kind of overspecified for this 2D robot. We really just care about linear in the x direction, which is the forward direction for this little robot. We'll leave the other 2 values at 0. And just the z-axis, the angular for just the z-axis, and leave the others at 0. Then when a pose update comes in, this method will be called. And so ROS messages are essentially, in the .NET world, ROS messages are an IEnumerable of name value pairs, ROS field values. And so you can parse that yourself. It's really just an IEnumerable. You can walk it. You can look for fields that are names you expect and get their values. There is a nice little helper method, though, this get dynamic field vals. So given this IEnumerable, it will create a dynamic for you. And so if you know the names of the fields that you're looking for, you can just pull them out. So we'll just get the X, Y, and theta. So this is just 100 lines of code. It's a very simple little class that can talk to ROS. So next, let's look at the turtle component. So this will be a proper Psi component, including the Psi namespaces, but this time not including ROS. Doesn't know anything about ROS. It's just a iSource component, which means that it can be started and stopped by the pipeline, and it's allowed to emit messages out of the blue, not in reaction to receiving messages. It'll hold on to an instance of the turtle that we pass into the constructor. And it will create a couple of a receiver and an emitter. The receiver for velocity is just the linear and angular tuple. And whenever it does receive such a message, it will just immediately pass that on to the underlying turtle velocity method. So that's quite simple. This single line of code just essentially passes through a stream of velocity updates to the underlying turtle class. And then for pose changed, we will create an emitter of this time a tuple of 3 floats, which is the x, y, theta. And to that you can post pose changed messages, which we'll see in a moment. So there's the receiver, and there's the emitter. And so when we start up, we connect to the turtle, and we connect to hook the pose changed event to call our onPose changed method. And then in stop, we just do the reverse, disconnect the turtle and unsubscribe from the pose changed event. Pretty simple. So on pose changed, all it really needs to do is, as long as the component hasn't been stopped, we post. So it's a very simple component. It's like 70 lines of code. Now the program is quite simple. The idea here is going to be, we're just going to read keystrokes and let you drive the turtle around. So here we'll just set the ROS node and ROS master addresses, and since they're on the same machine, we'll just use the loopback address. But they could be running on separate machines, and you can just wire that up that way. It's common to have a Windows machine running Psi and a Linux machine running ROS. So we create the pipeline, we create a new turtle component using that pipeline and a new instance of the turtle class underlying. And then for the pose change stream coming out of that turtle, all we do is just do a do and write to the console. So it's just going to stream to the console pose updates. Now the keys stream is an interesting one. We use generator's sequence to create a sequence of messages from this IEnumerable keys method. If we go look at that real quick, this is an IEnumerable of console keys. And that's generated just by sitting in a while loop and reading the keys from the console and yielding them. And that's it. Once you press Q for quit, then it breaks. A infinite, potentially, stream of keystrokes. Now, before we leave here, I think I'll write out the keys that you're pressing so that way you can see in the webcast when I'm pushing the arrow keys. So the idea here is going to be to take this stream of keys and just convert it to linear and angular values based on whether you're holding the up arrow, down arrow, or left and right arrows. So either just 1 or -1, depending on what arrow you're holding, or just 0 otherwise. And so it just returns this tuple of those values, and so it becomes a stream now of tuples of linear and angular values, which we pipe directly to the turtle velocity receiver. And we just run the pipeline. And that is it. This is the whole sample. It's pretty simple. Let's give it a try. I'll bring up our little turtle, and let's make sure that he stays in front while we're interacting with the terminal, and just run it. There you go. There's its pose updates constantly, and as you hold down arrow keys, you can drive it around. So that's about it. This is how simple it is to hook Psi up to ROS. And one of the beauties of ROS is that, like, this geometry twist message is a fairly standard message. You could swap out this sim for an actual TurtleBot robot and be driving physical hardware just as easily. Hopefully this has given you a good understanding of ROS and how Psi and ROS can work very well together. So that's about it for this session on ROS. I just wanted to point you at a few things to leave you with. So if you go to our GitHub and you go to the wiki, then you'll find on the right bar here, bridging to other ecosystems, bridging to ROS. So this is the jumping off point to find links to the tutorials, the one that we just went through, the arm control sample, some more information about the bridge, things like that. Then another one I wanted to point you at is if you go to the list of components, then there is pointers to other third-party repositories. That's just at the bottom of this list. But here's CMU. And here you will find a ROSBag reader for Psi. So this was an external contribution by a colleague of ours, Z, who was an intern with us. He's a PhD student at CMU, and so this is checked into the CMU repository. This is an implementation of iStreamReader, which is one of the ways that you can extend Psi to support other file formats. So this allows you to open ROSBags directly in Psi Studio, and also to use them as an importer in code. So hopefully you found this session pretty interesting. We learned quite a bit about how Psi and ROS can communicate and can work quite well together, complementing each other's capabilities in hybrid systems. Let's move on to the Q&A now. All right, so that was pretty fun. We did get one question in, but I want to remind people to go ahead and post questions, and we'll try to get to them in the next 10 minutes or so. The one question that came in was, does this current bridge work with ROS2? So ROS2 is a completely different protocol, completely different system. And honestly, no, this bridge works with ROS1 only. It was built some years ago before ROS2 was really underway. And we haven't upgraded it yet. That might be something we work on in the future. Obviously, ROS2 is the future of ROS. There is a bridge, though, in the ROS community, a package that will bridge between ROS2 and ROS1, so you always have backward compatibility. And it's my impression, I'm not deeply embedded in the ROS community, but it's my impression that the porting effort from ROS1 to 2 of porting all of these packages, the beauty of ROS is this ridiculously gigantic ecosystem of available packages. And the effort to port all of those to ROS2 is nearly infinite and probably will never be complete. So I think forever you will probably need to be able to bridge to ROS1 still. A lot of the most popular packages have been taken over, but there's a huge long tail of even abandoned packages that work fine or useful, but nobody's maintaining them, and they probably never will be upgraded. So anyway, this is ROS1, and if somebody wants to work on a ROS2 bridge, that would be great. That'd be kind of a help wanted topic we could add to our GitHub. If anybody needs help with that, we'd love to help also. And perhaps someday we'll do it. Let's see if there are any other good questions coming in yet. Not exactly. So, I mean, obviously, when we first show this, probably the most common question, the most basic possible question is, why would you use ROS? Why wouldn't you just build everything in Psi if you're working on a robotics solution? And, I can tell you a little story, basically. I used to be on the old robotics team, and we worked on indoor navigation using Kinect, and we built an actor model framework for .NET. We called it the reactive runtime. And so we built whole robots on, this framework just on .NET not using ROS at all. And I and another member of that team, Mihai, came over to the Psi team, and a lot of the runtime in Psi actually is inspired by that older system. So Psi, is basically built for robotics. The main difference, though, is that the ecosystem in Psi is more centered around human interaction, dialogue components and speech and that kind of thing. Whereas ROS obviously is the absolute de facto standard for any kind of robotics. Any kind of hardware that you have, there will absolutely be a ROS package for it. And that is the real beauty of ROS. And so, like you saw in the demo there with the indoor navigation robot that'll lead people to offices, obviously that needed a nav stack, but we didn't even use our own nav stack that we built on the prior team. We just used ROS because why not? That's not our focus at this point. We're working on the human interaction pieces, and we can get that off the shelf. So that's the beauty of ROS is, get this huge ecosystem of off-the-shelf components, focus on just the parts that you're interested in, and probably build those inside. Let's see, other things. ROS has, some tooling that we don't have, like Gazebo, a nice physics engine that's built in. That might be one reason to use ROS. Maybe we should partner with the AirSim guys and build something like that for Psi. Another help wanted topic, perhaps. But there's plenty of reasons to use ROS. We see them as, complementary systems. There's no competition here. We ourselves, of course, reach for ROS as a great tool when we need to do robotics.
Hey Ashley, there's a good question that just came in from Akansha about, so she asked, in your opinion on the limitations on the integration between ROS and Psi, any major points one should consider before integrating Psi and ROS for their particular project?
I don't think there are really any limitations. The API set for becoming a node in a ROS system is completely supported by the ROS bridge in Psi. So I think anything that any node written in any other language for ROS could also be written as a Psi component and bridged to ROS with no missing features, I don't think.
Yeah, I think the key, like you said earlier, is kind of do what makes, do what's easiest based on, what you already have in each ecosystem, like kind of, like in that example we had with the roaming sidebot, we didn't want to rewrite an entire navigation stack just for that in Psi. We had a great one in ROS, so it made sense to kind of merge those in that way. One question I think that we get a lot, Ashley, I wonder if you could talk a little bit about is there's a lot of places you can run ROS now these days, which wasn't always the case. You can have ROS just on a Linux box. Now there's the Linux subsystem for Windows where you can run ROS, and then there's even ROS for Windows. Do you have any sense on just even the differences between those and what we've tried in terms of bridging between ROS and those different on those different systems and what should work best and what might not work so well?
So I've personally tried, even for this demo, actually preparing for this demo, I tried running ROS on the Windows subsystem for Linux. And at that time, at least GUI support wasn't there. Now it turns out that just a few days ago, the WSLG has been released, or at least it's in pre-release. If you're on a certain Windows build, you can get it. As well as GUI support. And apparently a lot of the ROS tools like RViz and those things run on Windows in Windows subsystem for Linux, as a Linux build of ROS, but running on Windows. And then, yeah, like you say, Sean, there's a whole team at Microsoft doing ROS for Windows. And that all works also. I've played with that actually, with the Psi ROS bridge to the ROS running on Windows. That seems to work. And of course, it definitely does work using the Psi bridge to proper Linux build of ROS running on Windows under Windows subsystem for Linux. I've tried that as well. Just the GUI tools didn't work.
Yeah, so there's a huge combinatorial explosion, I guess, of places you can run Psi, places you can run ROS. I would also say, we haven't tried every single combination, so we'd love for more people to get their hands on this and try it out and let us know.
Absolutely.
what works and what doesn't work. There's another question that just came in, Ashley. How would synchronization and data fusion be affected from having some sensor streams coming from Psi and others coming from ROS? And I think that actually kind of connects nicely to some of the stuff you talked about with the Python session, but it should be similar for ROS, right?
Yeah, so yes, definitely. You could thread originating times through the ROS world and back. The problem is that, unlike Psi, where the originating time is part of the message envelope and it's absolutely guaranteed to exist on every message, the ROS world, the data schema doesn't even necessarily dictate that there is a timestamp at all on a ROS message, or that represents, originating time versus clock time, what clock time when the message arrived. So you might have to do some work on the ROS side to make sure that you're actually emitting sensor data that includes originating time from that sensor. And if you're passing data from Psi to ROS and back, you might have to do some work on the ROS side to make sure that those originating times survive the round trip. That's something that's not a primitive in ROS, essentially. So you can't depend on it existing without having to do some work.
Makes sense. I don't see any other questions right now. I think we have, I don't know, maybe just wrap up for 30 seconds.
Yeah. So the next session, Dan is going to do an awesome demo of HoloLens integration with Psi. So definitely stay tuned for that. That's coming right up. Thanks for attending the session. If you have any more questions, just keep them in the chat and we'll keep answering about ROS also. Thanks.
Hi everyone, this is Dan Bohush, and in this session I will be previewing a feature which we plan to release soon and which enables research using Psi and HoloLens. Now, I assume a lot of you are already familiar with the HoloLens device. HoloLens is basically a standalone mixed reality headset that enables immersive experiences. And as you might imagine, this is quite a complicated piece of machinery. It includes a plethora of sensors. It has 4 visible light cameras that are used to do head tracking, 2 infrared cameras for eye gaze tracking, a 1 megapixel time of flight depth sensor, a forward-looking RGB camera that can produce 8 megapixel stills or 1080p video at 30 frames per second, an inertial measurement unit that leverages an accelerometer, gyro, and magnetometer, as well as a 5-channel microphone array. It also includes speakers and has built-in spatial sound capabilities. Obviously, this device can produce a rich set of multimodal data streams. On the other hand, as we've already seen, Psi was designed to enable and accelerate the development of applications that process this type of data. So we felt it would be a great framework for doing development and research with HoloLens devices. As such, we created and plan to soon release a solution that allows for streaming data between a HoloLens device and the Psi application running on a separate PC. Now, to be clear, while in the future we plan to look into running Psi natively on the HoloLens device, for now, the approach we have taken is an interop one, basically, where we have a C++ WinRT application that is deployed to and runs on the HoloLens device. And this application streams data over a TCP connection to a Psi.NET application running on a PC. You all might be familiar or have already heard about the research mode for HoloLens, which gives access to key sensors for research applications that aren't intended for deployment. Our work basically leverages this research mode. In fact, our WinRT streamer application was built by evolving the stream recorder sample available in the research mode repo here. The streamer application sends the data over a TCP channel, and on the PC side, we have a Psi component called HoloLens to source that surfaces the various sensor streams produced by the device as regular Psi streams. The streaming happens in real time, and we can send information back to the device as well. So to illustrate this interop solution between Psi and HoloLens, I want to show you this simple small sample application we have built that was inspired by my grad school days. At some point during grad school, my roommate and I attempted to do a bit of a language exchange by putting post-it notes on various objects in the room with the name of that object in our respective languages. So as we were brainstorming what to build as a simple sample app for the HoloLens interop story here, we thought it would be fun and interesting to build this kind of experience in a mixed reality setting, where the post-it notes are virtual and appear as you basically look at objects. So next, let me walk you basically through how we build this sample and what it's doing. And rather than diving into code, I'm gonna start by first using Platform for Situated Intelligence Studio to show you the data collected by this sample app. Now, by now, most of you are probably already familiar with Resize Studio, but just in case you missed the previous session, this is a tool that comes with a Psi framework and allows you to visualize multimodal data streams persisted by Psi applications. I've already loaded a data store created by this sample app, and on the right-hand side here, you can see the streams available in the store. You can drag and drop these streams into this visualization area to construct complex custom visualization layouts, and you can change the properties on these various visualizers from this right-hand side here. The structure of the visualization layout is reflected in this tab at the bottom left. But let's now look at the store we've collected. Remember, the HoloLens is streaming the data live to the PC, where we have a simple Psi app that logged this data to this store and is doing the processing. You can see here the list of raw streams coming out of the HoloLens source component. I've already created this layout that visualizes these streams, so let's look at them step by step. I'll start by first hiding all these visualizers in the layout, and next I will bring them back in and discuss them one by one. So from the HoloLens device, we get a stream of images from the forward-looking camera, and that's shown by this visualizer. We also get the track 3D head position and the vertices of the aggregated surface of the world that the HoloLens is building. These streams are visualized here as this 3D coordinate system for the head position, and the point clouds shows the surface map vertices. Basically, you can get a sense of the structure of the room I collected this data in. Because we also have information about the location of the PV camera in the world, the camera image, as well as the intrinsics, we can quickly assemble and visualize a 3D camera view. Resize Studio includes visualizers for this type of views. And now, as I play back through the data, you can see how the head moves basically around the room. Let's go back to the start though. HoloLens also provides the depth image perceived moment by moment by the depth camera, which is rendered here as a blue point cloud. We also get the direction of the gaze, and I visualize this as well as this orange ray. Next, we intersect this orange ray with a depth map, and here's a visualization of this intersection point. And then we project this point back into the color image, and here's where it lands in the pixel space. Next, we crop a region around this image, and we instantiate and run a ResNet 50 Onyx model to do object classification. We take that result and pass it along to another Psi component that wraps the translator Azure Cognitive Service in the cloud for doing machine translation. And here's the results now placed spatially next to the object. In this case, it's pretty close. It says Libro Jacka, which is a book jacket. And we send basically then this information back to the HoloLens and display it as a virtual post-it card. And this is shown here in the stream that displays the mixed reality capture from the HoloLens. It's a bit difficult to see in this image. This text looks a little bit better inside the actual virtual world in the device. Now, all of this runs in real time. And as you can see in this playback, as I look around the room, various objects are being tagged. Of course, this is far from perfect. The object detection is quite noisy, and in this case, I've just used completely off-the-shelf model. There's quails and ping pong paddles detected in here. But really, the point I'm trying to make here is not about computer vision or the accuracy of the application. It's more about the fact that using Psi, you can really quickly prototype this type of multimodal integrative AI applications that process data coming off of the HoloLens device. And let's actually take a closer look at the structure of this particular sample app. The app uses this HoloLens 2 source component, which provides access to all these different streams. We first take the image streams and fuse them and assemble a stream combining all the information about the PV camera view. Similarly, we fuse the depth streams to assemble another stream containing all the information about the depth camera view. We use this latter stream in conjunction with the eye gaze information to compute the location of the gaze target. That is, where is the 3D point where the gaze direction intersects the depth mesh. This information is then brought together with a color camera view to project this 3D point in the 2D color image space and then crop a smaller image around it. We pass that resulting image to a ResNet 50 object classification model and then pass the results of object classification to the Azure Translator cloud service to perform translation. The results of this translation are fused in a synchronized manner again with a corresponding computed gaze target to construct a stream that describes both the location and the translated name of a detected object. Now, as you might imagine, these two different streams arrive here at different latencies, as one involves running a DeepNet model as well as a trip to the cloud, whereas the other one arrives on a more direct path. Psi provides the primitives for quickly resynchronizing and aligning these streams according to originating times, regardless of the wall clock delays involved. Finally, these results are aggregated here over time, producing a stream that describes a collection represented as an array of objects with their translated names. This information is sent back to the HoloLens device via TCP writer component, and in this case, we modified the WinRT stream server app on the HoloLens side to take this and render it as virtual text nodes using DirectX. We focus, though, here mostly on the input processing side, and so I won't dwell on this output part much more, other than to say that in the long run, we are looking to evolve this story more and construct a more formalized way of projecting information back towards the HoloLens device. The high-level point here, though, is that the beauty of Psi is you can author this type of multimodal processing pipelines relatively quickly. For instance, creating the HoloLens 2 source component takes but one line of code. You basically have to specify the IP address of the device, and in this case, the image decoder to use, since we're compressing images in transit to send bandwidth on the TCP channel. Instantiating the ResNet object detection model can also be done very simply. We create a new image model runner Psi component and configure it in this case with a path to the corresponding Onyx model and the class label file. Similarly, the Azure Translator cognitive service can be instantiated with one line of code by passing it the service subscription key and the target language for translation. Finally, connecting all these components together is also relatively straightforward, even when two components were developed completely separately and their inputs and outputs types might not exactly match. So for instance, in this case, the ImageNet model runner component produces a stream with its own custom classification results type, and the translator component expects, however, a stream of strings. To connect the two, we can simply inject this select stream operator in the middle that allows us to transform the labels coming out of the ImageNet classifier into a corresponding string, which we then simply pipe to the translator. Now, while the Psi ecosystem contains a number of sensor and processing components like these, and hopefully this set will continue to grow and evolve over time via community contributions, I should say that, of course, you will not always find exactly everything you need for your application off the shelf. So for instance, in this example, we had to write some custom code to compute the world position of the gaze target. And even that, in this case, was actually not too complicated. Here's the code for this computation. All in all, hopefully it's clear by now that Sai allows you to basically write and quickly prototype these kind of pipelines and glue various off-the-shelf and custom stream processing components in a quite compact manner. The second point I wanted to highlight is that the framework also enables quick iteration and tuning. Once you get the data over to the Sai application, you can easily persist streams to a store by simply invoking this write operator, like in this example here. And then you can use the data collected to replay to iteratively develop and tune the various components and the pipeline for your application. So basically, instead of using the HoloLens and debugging live, you can rerun based on persisted streams from a store as if you were connected to the device. This capability is very important and accelerates a lot of R&D work, as chances are it will take a bit of iteration and tuning to get something to work very well. Okay, so this brings me towards the end of this brief presentation. And before we open it up to questions, I wanted to reiterate that while these components and sample are not yet available in the repo, we plan to release them soon, so stay tuned to the repo. Also, I wanted to share a bit more about our roadmap in this space. We plan to continue to extend the source component to include other streams available from the device, such as audio and IMU data. And as I've already mentioned, we hope to develop more the output story as well. We also plan to look into creating the ability to run Sai pipelines directly on the HoloLens device rather than this interop story. And we'll continue as well to build additional samples and demonstrators. We're looking forward to hearing from you guys on what are the types of features you'd like to see in this space. And with that, thanks again for listening to this session, and let's move on to questions. Hi, everyone. So thank you again for listening in on this session. I've been monitoring the chat. I haven't seen yet, I think, any questions arrive. So I'll give a few moments here and remind you guys, feel free to type in questions on the way as these sessions progress. I hope this was interesting. We are excited about this space. I think there's a lot of opportunities here, given the nature of the HoloLens device and the type of streaming data it produces. And given, on the other hand, the affordances of the Sai framework, it seems like a very good coupling here in terms of sort of quickly prototyping experiences, doing research. And we're planning to kind of invest more in this space and grow this sort of in this direction. Would love to hear, as I mentioned, from you if you have use cases of this nature or things involving, you know, the HoloLens 2 device, like how we can better support it in Sai. Yeah. I see there's one question that just arrived that let me just, are there any, from Shelly, are there any resources for other AR headsets, such as Magic Leap? And the short answer to that is right now, no. But I think if that's an interesting direction, we could look in that direction as well. Definitely this whole world, again, of mixed reality or augmented reality couples very well with the capabilities of the Sai framework. So we don't have something at the moment. If there's interest in that, you know, feel free to open like a feature request issue on the GitHub repo, and we can consider that and time it with everything else. I'm not sure. I think our main focus, to be honest, right now will be on the HoloLens device for a while, but definitely would be good to know from the community if there's you know, other headsets that people are interested in working with.
Hey, Dan, there's another question kind of along the same lines that's more about VR. Like, have we thought about integrating with VR headsets as well? Or?
Yeah, so I think the same answer that I kind of alluded to. Not much, not yet. One other direction that we're kind of looking that perhaps relates to the VR world is Unity integration, right? A lot of oftentimes development for these VR systems is done with Unity. So we looked a bit in that direction as well, and we might have some bridging and componentry, and then the ability to interoperate with Unity as well, some nearby future point. But we haven't looked specifically, concretely on hardware, on the hardware side, on specific headsets and what the SDKs or what the, you know, how those things look like. Yeah.
Then Question that just came in. This is a good one. Are there any other components under development to support activity recognition from the first-person perspective, like HoloLens 2, like recognizing hand gestures and movements and things like that?
So definitely that's the direction we're heading into,
Yeah.
So we, in our own research, we are, apart from the infrastructure work, and Sean will talk a bit more about this in a session that I think, is it after lunch, Sean?
Right after lunch, yeah, we'll talk.
Yeah, so there's going to be a session after lunch where we talk more about perception of humans and, a toolkit we're developing for building systems that reason about people in physical space. And definitely in that context, especially, we are looking also at starting to build models from first-person perspective and also for data fusion, even in scenarios where you might have fusion of first-person kind of like a VR, AR headset plus cameras around it. But stay tuned. I think it will be an interesting conversation in the presentation that Sean will be giving like after lunch in that direction.
I'm not going to talk a lot about the first-person perspective, but certainly the fusion of multiple, outside-in, third-person perspectives from multiple cameras. But like Dan said, we're really interested in moving into that space of not only just, what can you do from a first-person perspective, but how can you combine inside out and outside in to do this broader activity recognition. I think it's a really cool space.
And this is where we would love to also see like more community contribution. So, if you're interested in that space and you're perhaps yourself developing some models, or, perhaps you're focused on one aspect in that space and you need something else, let us know, hey, I'm working on this and I need this, and so on. We would like to kind of get more engagement with the community and connection points to kind of understand, how we take this forward and how we grow that ecosystem.
We have another question that just came in specifically about, do you have any information about interoperating with Unity, either with or without HoloLens 2?
So I don't know, Sean, if you want to talk a bit yourself to that.
Basically, no, I mean, it's something that we are working on and we've explored a little bit. We haven't gone too deep into it, but it's something that we're really interested in supporting. Like you said, it's not just for HoloLens 2. I think there's a lot of reasons that you'd want to interop with Unity if you have a lot of avatars and virtual characters that are being animated in Unity, or Unity is just a really great platform for doing some of this animation and game engine type of work. And then of course it has support for all of these different VR headsets and AR headsets. So it's something we're really interested in. It seems in theory that it should be not too difficult, in that you can program your modules and different components in Unity in C# and .NET. We've run into a few snags in terms of running Psi on, letting Unity drive things and having a Psi pipeline run, because Unity has some strange ways that it does. It uses mono, and it has kind of some there's some conflicts with how we do serialization and some of the runtime stuff now. I think we can get to, at the very least, an interop story where you have Psi on one side and Unity on the other, and they're talking to each other. But we are interested in looking deeper into kind of having that be a deeper integration. But this might be another thing where we write kind of a help wanted topic and engage the community on kind of getting some community contributions on that, especially from people who have probably a lot more experience developing for Unity than we do. So. But it is something that we're super interested in.
I see another question that came in on, is latency an issue with the current TCP setup between the HoloLens and the Psi device, or the machine where you're running the computation for real-time applications? And the answer to that is we're still exploring, kind of. So I'll be completely frank, that we haven't yet released this, and we're going to push it out there in the next few weeks. Basically, right now we are doing the timestamping at origin on the HoloLens side, and we're forwarding those timestamps to the Psi world. And Nick, jump in if I'm saying something wrong here, but I think basically, and in the small sample that I just showed you, where we're kind of tagging these objects in the world, depending on where I'm looking, it looks pretty responsive, and that's a round trip all the way back to the HoloLens, right? So I haven't perceived directly a big latency issue. That's not to say that you might not run into them. You're talking over a network connection perhaps, or over a USB cable, and so
it's possible. And so I think this is going to be a learning experience for us also a bit as we move forward. How reactive can we get that interop story to actually be? I think it's a good question.
And then there was a question about are there components or plans for integration with simulation environments or simulators like iGibson, Habitat, etc. So that's interesting. Like I'm not familiar with those specific simulators, but it is actually something that we're kind of interested in a research sense of getting a little bit more into. I'm kind of becoming interested in simulation. I think one thing that we'd love to integrate with that makes a lot of sense is AirSim, which is this other open source project from SAR, a simulation environment that's in Unreal and I think also in Unity these days, mainly for as an environment for training self-driving car scenarios. But it's something that is also out there. Look it up on GitHub, and we'd love to have kind of integration between that and Psi. But we haven't done anything yet. But it's definitely kind of a cool area that we'd love to look further into. Dan, there's this question about, so one of the features of ROS is the ability to have these common or custom messages between distributed nodes. Are there common data types for the Psi ecosystem? So like messages that can be used for HoloLens and other devices, and like,
yeah, so
just a little bit about are the restrictions on the messages that we send around.
Yeah, so the nice thing about Psi is that in some sense, like it's a .NET framework, and we spend quite a lot of effort and energy to make sure we can serialize basically pretty much largely any .NET type. So you're not very restricted. You can pretty much stream around most .NET types with some minor exceptions. And so now in terms of standardized types, some of the Psi packages, like for instance, if I think of the Psi imaging package that does, contains componentries and API for processing images, we have our own Microsoft Psi image kind of type that we use often when passing images around. And for instance, the bridge to HoloLens talks on a TCP channel and the bytes come in, but on the Psi side, you just see a Psi image that you can process to all sorts of Psi components. So throughout various, I guess my answer is throughout various Microsoft Psi areas, like packages, like audio, imaging, and so on, there are some base types and some base representations. But one of the features of Psi is actually the ease with which it lets you glue things together, even if they don't type match. You can very quickly transform a stream of some type into a stream of some other type. It's very quick to wire these things together. And so we built Psi kind of as a research framework, at the base, and we wanted to retain a lot of, and this is just from an engineering standpoint, quite a lot of flexibility to not constrain things very and pin them very down, but make it easy to actually glue and connect things. I hope that kind of answers. I'm not sure if I'm answering exactly the question, but hopefully that gives you a sense.
I think so.
I think we're at about time here, probably, or a little bit over even. So we can continue answering questions in the chat. Feel free to post more questions about this HoloLens interop story. But let's move on to the next interoperating story. And Sean will be talking about integration with Microsoft Teams this time.
Hi, everyone. So in this short session, we wanted to share a quick preview of some things we're working on to integrate Psi with Microsoft Teams, so that people can utilize Psi's powerful infrastructure, components, and tools around multimodal data processing in order to quickly prototype new kinds of intelligent bot applications inside Teams meetings. And we feel that being able to use Psi in Teams bot development could really lower the barrier to entry on conducting research on smart meetings, AI-supported remote collaboration, interactive meeting facilitator agents, and so on and so on. And in this session, I'll talk a little bit about how we've implemented interoperation between Psi and Teams, describe the development cycle that one might follow to implement Teams bots with Psi, and preview a small sample bot application that we've built ourselves. But to start off, let's clarify what Teams bots are and what they can do today. Because there are a few different kinds of bots that people talk about. The most common kind of bot you'll see in the Teams ecosystem today are these simple chat bots, which you can install and chat with in your Teams client. And they can help automate certain tasks for you, like automating the scheduling of meetings, or sending out polls to people in your organization, and so on. But we're not going to be talking about those kinds of bots today. Instead, we're going to focus on bots that actually sit in on live meetings, with access to the audio and video streams coming from each participant, and potentially even generating its own audio and video streams to participate in the meeting in some specified role. So for example, this bot might passively sit in the meeting and do some processing and analysis of all the audio and video coming from the human participants. Perhaps the bot could then send participants a summary of the meeting after it ends, including which agenda items were covered by which people, or how equal and inclusive the meeting was in terms of time spent speaking by each participant, or really anything you might think of. And this kind of passive bot would still show up as a participant with an icon, as you can see with this hexagonal icon down here at the bottom next to all the other participants. But that's all. That's the bot's only presence in the meeting in this case. Going further, a bot could produce a video and/or audio stream and actively participate in the meeting as a rendered avatar with synthesized speech. And going a bit further yet, a bot could activate screen sharing mode, essentially taking over the view that everybody sees with its own rendered graphical presentation as if it were sharing its own virtual screen. Now, to build bots like that today, you can use the Microsoft Graph Communications API, which powers Teams under the hood. And this is a GitHub repo that already contains a few samples that you can follow to get started building your own Teams bots today with this SDK in .NET. But we've recently constructed our own bot sample using those other samples as a jumping off point, but really to show how Psi can be used inside the bot architecture to handle all the audio, visual, processing, and intelligence. And we'll release that sample in that group Graph Communications GitHub repo shortly after the conclusion of this workshop, so look for an announcement on that very soon. So here's a short recording of what our sample Psi bot can do in a live Teams meeting. So this sample bot hosts a Psi pipeline inside of it, which is fed with each participant's video and audio streams. In Psi, we do some simple voice activity detection by calculating the log energy on each audio stream and accumulate over a window to determine which participant has been speaking the most at any point in time. We also assemble each participant's video stream and construct sort of the circular layout of video thumbnails and render this purple ball that gravitates towards the most active speaker at any particular point of time. Now the Psi bot here is emitting a video stream of this rendered layout you see for its screen sharing output, and that's projected here as you see in the Teams interface. And I want to point out this idea was inspired by some old work from Sandy Pentland's lab at MIT Media Lab on the meeting mediator and other related projects that they've done. And the main idea really is just to implicitly promote more inclusivity in meetings, because of course if one person is dominating, they'll see the ball is stuck to them. Here I'm seeing the ball kind of get stuck to me. But if participation is equal, then the ball will kind of hover nicely in the middle, which is what we all want. And this is just one small example of the kind of Teams bots one could prototype quickly with Psi. And the important takeaway here is not necessarily this specific example with the bouncing ball, but really the general architecture underneath of how we enable this and how you can use Psi with Teams in your own research and development on meeting bots. Psi is a powerful platform for dealing with multimodal streams of audio and video data, processing such streams, and synthesizing resulting streams. So we really believe it's a great fit for prototyping, researching, and experimenting with these kinds of intelligent meeting experiences and bots. So let's take a closer look at the underlying architecture of how we integrated Psi with Teams next. So in a typical meeting, we of course have 2 or more human participants connected to a Teams server in Azure using their particular Teams client on the desktop, on mobile, in the browser, whatever. And then a Teams bot is essentially an automated participant in that meeting. So it interacts with the team's infrastructure through web APIs and sockets, more specifically the Graph Communications platform that I mentioned earlier. And most likely this bot is hosted in Azure also, with access to and from Teams. It interacts with Teams as a client, much the same way that humans do, joining meetings, chatting, viewing and listening to participant video and audio streams, and interacting through its own audio and video output. A bot can have all the same kinds of communication issues that a normal client can have, such as dropped video and audio. And being hosted in an Azure data center with a good connection helps, but there's really nothing special or first class about being a bot versus being a normal participant. They're just another client in the meeting, and it's good to kind of keep that mental model in mind. Now, we integrated Psi into Teams bots by actually hosting a Psi pipeline inside the bot architecture. So a layer of boilerplate code is provided that handles that communication with Teams, establishing calls, exposing hooks into all of the participants and the bot's audio and video data. And all of this data is distilled and passed to and from your specific Psi pipeline of componentry for your desired application functionality via this interface named iTeamsBot. And the idea is that it abstracts away a lot of the bot complexity and lets you operate at the level of Psi streams. So let's zoom into what that interface provides. For now, it exposes 2 input streams and 3 output streams. So the Psi pipeline implementing this interface will have 2 receivers for consuming the participants' audio and video streams. Notice that these input streams are of type dictionary from string to shared of image and dictionary from string to audio buffer. And these represent data that's keyed on each participant's ID, which represents the participants in the meeting as they join and leave, or turn on and turn off their cameras and microphones. And processing those dictionary streams is very naturally handled by this parallel operator that we have in Psi. Now, this interface also allows your Psi implementation to produce audio and video output for the bot. So it has video out and audio out, and it has a separate emitter for screen sharing, which is also a shared of image output. So zooming back out here, it's important to point out that there's a significant amount of overhead in deploying a Teams bot up into the cloud each time you make changes to it, scheduling meetings for testing, debugging it while you're in a live meeting. And so even when you're past that initial boilerplate setup of registering your bot in Azure, making sure it has all the right connections to communicate with the Teams infrastructure, all of which, by the way, this is documented in the existing samples, and it'll be further documented in the README for the sample that we'll release shortly. Even when you've done all of that setup, iterative development can really be slowed down by this non-trivial overhead in deploying to and from Azure. But here's where another really important feature of Psi comes into play and can really accelerate your work. So as we've discussed a lot in previous sessions, a key feature of Psi is its ability to do performant logging of all streams to a data store, which can then be used later in replay and tuning scenarios. And a Psi Teams bot enables exactly that. You can log all inputs and outputs to a Psi store, so you can collect data from one or more live meetings, then work offline and iterate quickly on developing and debugging the bot further. This log data can be used locally outside of Teams to replay to the bot using a testbot app, which is provided along with the sample. Previously recorded meeting data is fed into the iTeamsBot instance locally. This app also renders the bot's output as well as rewriting to a new store for further analysis in Psi Studio. Being able to iterate offline is a huge benefit of Psi, avoiding the time-consuming process of repeatedly publishing iterations to Azure and arranging test meetings and so on. You can, of course, bring all of your meeting data into Psi Studio then once you have it in a Psi store And you can look at all of your participants' video and audio streams side by side. So here we're showing, all 4 of our participants' video streams side by side with the separated audio track for each participant. And we can scrub through that and do everything inside Studio that we can normally do. And then you can quickly explore other ideas and designs for your bot's implementation and behavior. So here, for example, we look at emphasizing speaker activity, not with a bouncing ball, but by scaling video frames. And we're testing this design over the exact same meeting data that I showed earlier. Like I said, publishing the bot up into Azure, it just takes a few clicks, but it does take 5 or 10 minutes to actually finish deploying. And so that, having to do that repeatedly while working on a bot is tedious, and it can really slow down iterative development. So that's why this logging and replay capability alone may be reason enough to use Psi for Teams bot research and development. You can iterate quickly, you can compare alternative designs side by side in Psi Studio. Here we're comparing side by side the bouncing ball at the bottom with the scaling of thumbnails up at the top. And generally this just allows you to focus more on the fun part of developing new capabilities for collaborative meeting bots. Now, of course, this initial implementation and sample barely scratches the surface of what's possible, and possible extensions could include, adding text chat features to the Psi interface, in addition to those video and audio streams. Adding support for rendering a virtual avatar face for the bot to have, so it can have its own presence in the meeting. And any other kind of smart meeting capabilities, samples and demonstrators that you might think of. So we definitely hope that others will be able to pick up from what we've started with this sample of Psi Teams integration to build your own features and experiences, and then share them back with the Psi and Teams communities. So hopefully this gives you a taste of how Psi is a great choice for Teams bot research and development, from the available components to the streaming runtime, to a simplified bot interface, tools for dealing with and visualizing data, and quickly iterating with data logging and replay. Psi is really well suited to research and development of multimodal interaction in both the physical world and in virtual meetings. So I'll stop at this point, and I'm curious to hear what you think, and happy to answer any questions you might have. Thanks. Cool. Well, I hope you enjoyed that little preview of some stuff we're working on to interop between Psi and Teams. Like I said, we're hoping to release that sample that I showed online on GitHub, hopefully soon. There's still some cleanup and documentation that we need to finish. And one thing that I want to reiterate is basically that what enabled us to do all that is that there was already this Graph Communications API SDK out there with some samples on GitHub. The team over in Teams in Microsoft, in collaboration with some other people at MSR, has come up with some great samples on how to get into how to hook into the video and audio streams that are coming from Team programmatically. And what we've done is put Psi in the middle of that, because again, that Psi is great for processing multimodal data, video and audio. So we've made it possible to put Psi in that existing Graph Communications and Teams architecture. And again, one of the main benefits here is that you can then persist data, iterate offline. And it was that, was super essential for us to even develop this sample itself that you saw, collecting just 1 or 2 live meetings and then iterating offline much more quickly than if we had to constantly schedule new live meetings and iterate more slowly. So feel free to ask questions in the chat.
There's a couple of questions, Sean, that have popped up. So one question from Ken is, how about ink for whiteboard in Teams or Surface Hub?
That's a great question. We haven't looked into it ourselves, but we would love to add or support someone who wants to add more support for that. I think it should be, I guess I'm not too familiar with the SDK for ink, but I assume it should be fairly straightforward to write components for ink, and to have that integrated into Teams. Like I said, like right now we have the video and audio streams kind of input and output. Something we don't have is the text chat, which we would love to add, and then having ink input, or just even the drawing, collaborative whiteboarding go in and out of the Psi pipelines would be awesome. We haven't looked into it ourselves yet, but
it's another question on, does Psi take into consideration, take care of the latency introduced by the internet connection? While most connections might be 30 to 100 milliseconds, some might be 500 milliseconds or more. So I don't know what's the latency, exactly in these cases.
Yeah, I don't know. I might ask Ashley if you're available, like what your observations have been of latency. I mean, obviously we're timestamping at origin like everything else with in Psi and having originating times, but Ashley, do you want to speak more to that?
Yeah, so the Teams API basically doesn't give us originating time at the client.
Yeah.
The human on the other end. So we're just stamping originating time with the time that it arrives at the bot in the cloud. So that's basically the best effort we can do with the information we're given. Also, even if they did give originating time at the clients, then you'd have a problem synchronizing clocks among all of the clients, and none of that's been solved. So we basically do our best effort just based on the time that it arrives at the bot.
Cool. There's another question from Z that says, that's a really cool demo. I was wondering if you all have any thoughts on the difference in running Psi locally and on Azure.
So you mean running the bot locally and running the bot on Azure and running Psi? So in our development so far, again, I'll let Ashley maybe speak a little bit to that as well. We've found the most success in running the bot itself in Azure. I know that there are ways to run, and again, this is separate from Psi right now, running your Teams bot locally and using things like ngrok and whatever to kind of send messages back and forth over, open up ports. It's a little bit complicated to set up, and we had a little bit of trouble getting that to work. So we had the most success running the bot in Azure, and then by extension, hosting Psi in Azure, and then the bot is kind of right next to the team server in Azure. But I'm not sure we haven't successfully set that up yet to have the Teams bot run locally to make any kind of comparison. So that's just where we've had the most success so far. But again, this would be great once it's for other people to try this, and if they get some of these other setups working, and to contribute back some insights and kind of the best way to do that. It'd be great to collaborate on that.
There's another question from Raj, which I'm not sure if we have the answer, if you guys know, but if not, maybe we can get back to him later on. Does it support IncML W3C? I'm guessing that's some sort of W3C standard, or like I actually don't. I'm not familiar with that, but
yeah, I'm not sure if there's a .NET SDK. I'm not familiar with it, but
yeah.
It's one of these things that if there's like a NuGet, especially, or if there's .NET SDK for it, it should be very easy to support and to again kind of either add a separate component for it or to integrate it into this bot sample. But we haven't looked into it ourselves.
I noticed also there's a comment from Chirag more back to the Unity story that a simple way to go there is to do interop, like kind of we showed with Python, and certainly that's something that can be done. I think it's a common that I think it's something that would work. I think we'd love to get both solutions, ones where you interop and one where you can actually run inside Unity.
Yeah. One thing. Oh, there's Microsoft supports that in the Office product, says Raj. Great. So I assume we just need to look into it more. I'm sure with IncML that it can be supported. It's just another component that we'd love to add, and maybe it'd be another opportunity to have a help wanted topic and engage the community on adding some support for Inc and IncML. One thing I wanted to say, and please keep writing questions, but one thing I wanted to say, and with regards to the Teams bot sample here, is to develop and deploy your bots responsibly. So we're going to have pointers to documentation around that when we post this, and just kind of best practices. But you know, there are concerns about having bots floating around that are recording meetings, and you know, in this case, it's going to be recording to Sai stores. If you've ever been, you know, in regular Teams meetings, if someone clicks, you know, record, you'll see that a little notification comes up at the top for everyone that they can see, okay, someone started recording this meeting, so I can know, you know, whether I feel comfortable or if I want to leave or say something. So you kind of, you know, it's best practice to give people some kind of notification when you're writing and deploying these bots, if you are going to be persisting to these size stores. I think that's best practice. So, you know, everyone is always aware if there's any kind of recording going on. In terms of the bot's presence, which is a good thing is you can't hide its presence. Like, it'll always show up with an icon at least, and you'll see that there's a bot in the meeting. But it is best practice to kind of make people aware if you are persisting and recording the meeting. So like I said, we'll have pointers to best practices and documentation on that with the sample. And then I don't see
it.
Anything else. I think we're close to time, or no, we have 5 minutes, I suppose. Wait for just a second, but yeah, if there's no more questions, I think we can probably go to lunch a little bit early, just a few more minutes. But yeah, we're really excited about this integration with Teams. You know, there's obviously a ton of interest in doing research and prototyping of these, you know, remote meeting experiences for good reason over the last year. And we just really think that Sai could be, you know, an accelerator and an enabler to kind of prototype some really cool meeting experiences more quickly. So we're really excited about that space and excited to engage with people and collaborate when we have that out on GitHub soon. So with that, I think we can go ahead and break for lunch. Let me just say really quick, we're going to post an announcement to the post-event survey now. So if over lunch you want to fill out that post-event survey, that'd be great. We're also going to post another link at the end of the event, and we're going to send emails around to the registrants so you have that link in your email as well. But yeah, it'd be really helpful if you guys could take 3 to 5 minutes to fill out that survey whenever you get the chance. Other than that, have a good lunch, and we will see you back here for a session on Situated Interaction Foundation after lunch. See ya. Hi everyone, thanks for sticking around, and I hope you've been enjoying the workshop so far. In this final session, we're going to preview a higher level framework of components, representations, and inference models we're currently building on top of Sai, and which are meant to serve as a foundation for building a particular class of situated interactive system. We call it Situated Interaction Foundation. An initial release will be out on GitHub within the next few weeks, and we'll continue to add to it moving forward after that. But just to recap a bit from the past 2 days, Sai itself is a very general platform. It's useful for building a broad class of systems. Basically any kind of system that integrates multiple component technologies, AI or otherwise, and works with multimodal temporally streaming data could benefit from Sai's affordances. And hopefully that's been clear from all the sessions over the past couple of days. As you've seen, the core infrastructure is great for dealing with issues having to do with time, synchronization, and latency awareness. It has powerful tools for debugging and visualization, and it has an open and extensible ecosystem of components. So because of all that, we believe Sai can be really useful for accelerating the development of all kinds of systems like that. So you could, for example, imagine building an array of IoT devices to sense and make inferences about temperature, sound, and light levels in a room. Or doing batch processing and semi-autonomous annotation of multimodal data sets. And those are really great use cases for Sai. But in addition to doing engineering and development of Sai itself, and supporting a community of developers around it, we are also a group of researchers asking some basic questions in the space of situated interaction. And in particular, we think a lot about this question. How can we enable machines to reason about and interact with people in physical space? And in attempting to answer that question and building real interactive systems that we deploy in the wild to help us answer that question, that's basically, that's some of the original motivation for why we embarked on building Psi several years ago in the first place. And Eric kind of alluded to some of that in his opening remarks yesterday. Before embarking on the Psi project, our group built and did research on several situated interactive systems, basically cobbling together whatever infrastructure was necessary along the way. So for example, there was this embodied virtual agent system that served as an assistant outside of Eric's office. It could interact with visitors and let them know when Eric was likely to be available, take messages for him, handle calendaring, and so on. We've also done several research projects with these stationary Now robots, which we designed to give directions to people to other places in our building. In this project, we were exploring how the robot might reason about the user's attention and strategically use hesitations, disfluencies, and interjections to recapture a person's attention when it was detected to be somewhere unexpected, and therefore coordinate in a more fine-grained way to complete its directions-giving task.
Do you need help finding something?
Yes.
Could you tell me the room number or person you're looking for?
I think it's 4800.
To get to 4800.
No, I think it's 4300. 4300, yeah.
Excuse me.
4300.
Go along that hallway.
I'm looking for 4300.
4300 is just down that hallway and will be the first room on your left.
Okay.
By the way, would you mind swiping your badge on the reader below so I know who I've been talking with?
Another project with these directions robots had to do with proxemics and physical space, and we explored how the robot might take explicit actions to shape the social scene in ways that would make it easier for the robot to sense and interact with people.
Now, where's the cafeteria?
Sorry, but if you don't mind taking one step back, it may be easier for me to... Perfect. Thank you.
Nice.
Now let's see. Can I help you find anything else?
So hopefully that gives you an idea of the kinds of systems and some possible research questions I'm referring to when I talk about physically situated interactive systems. These are systems that can reason about and act within a physically situated context and interact with and around groups of humans in the open world. And Situated Interaction Foundation is a framework that simplifies the construction of this kind of end-to-end situated interactive systems to allow researchers and developers to focus attention on their problems of interest while easily leveraging the work of others. And think of it as a layer on top of Psi, because while Psi provides fundamental building blocks we need in terms of the streaming infrastructure, plugging generic components together, tools for visualization and debugging, everything you've seen in the past couple of days, there's still a fairly large gap in requirements to get to the point where we can simplify the development of these types of physically situated interactive systems. And so to build them, we need representational primitives to model and reason about interaction. And so we draw from research in areas like collaborative activity theory, sociolinguistics, and context analysis to create those. We of course need an array of components that enable reasoning about humans and the activities of humans in the world. And finally, it will help to have a baseline architecture for how these components come together so they can be leveraged across specific applications. So Situated Interaction Foundation, or SIF for short, as I'll call it a lot, is meant to provide these affordances, in addition to the tools already provided by Psi, like Psi Studio, for visualization and debugging. We're designing and developing Situated Interaction Foundation with a few high-level principles in mind. So the main idea is that using SIF, you as a developer can simply specify what sensors you have and where they're located in space, and maybe some of the other big objects around that define the topology of the space. And the framework will automatically configure a perception pipeline to make inferences about people in the scene and construct a moment-by-moment understanding of the situated context, providing you with a rich set of representations to leverage when constructing your own particular application. So for instance, in the video on the right here, we have some example data we've been collecting with a SIF pipeline. In this setup, we've defined some large objects in the room. We have two Azure Connect cameras that are looking into a kitchen. The room is a kitchen in this case. You're seeing the Azure Connects show up as frustums here. And the two people are involved in a collaborative cooking scenario. And they're working at this kitchen island here at the center. But this is just an example. SIF is completely agnostic to the particular scenario, but this is a real example of data we've collected and iterated on ourselves as we continue to develop the capabilities of SIF. Now, the first important principle of SIF is that instead of having to start with image pixels, depth maps, audio buffers, even raw skeletal tracking, instead you can build from higher level rich representations of 3D objects, actors and their locations over time, attention directions and targets, actions and activities, both individual and joint. And you're seeing some of those visualized here. And these representations are continuously streaming over time as Psi streams for the developer to leverage in their application. And there are both spatial and temporal dimensions to these representations. Spatially, information about both relative and absolute positions of the various entities in full 3D is available. And similarly, temporally, the framework provides not just an instantaneous slice, but a full historical picture of everything that's come before at every time step. And I'll provide examples of that and why it's important shortly. Another key principle is to perform fusion when multiple views are available. So if you have one sensor pointed at your scene, SIF will do the best it can with that to build up a representation of the situated context with everything in it that I just mentioned. But if you have multiple sensors, and as you see here we have two sensors, we can fuse information across them to get a more complete, robust result. So for example, in this scene, you're seeing two sensors pointed into the scene, and I'll illustrate some examples shortly on what that can achieve. In principle, the more sensors you have, the more robust the results should get. And the final design principle is that we want SIF to be easy to use and customize. So if you want to get up and running quickly with building your own situated interactive applications, you can simply instantiate a SIF perception pipeline and you're off to the races. You can build directly on top of these rich representations. But while in the base implementation, we will provide a set of default models for each of these inferences, the models themselves are customizable and completely replaceable. So if you want to focus on developing particular pieces yourself, say you're a vision researcher interested in improving body tracking models, or you're a speech researcher developing better speech recognition modules, we're making it easy to configure and customize any and all portions of the SIF reference architecture, so you can rip components out and insert your own, but then test within a full end-to-end system without needing to implement all the other parts yourself. Now let's take a closer look at what we've implemented so far in the SIF perception pipeline, starting with inferences about body pose. So as I hinted at earlier, in this example, we have two Azure Connect sensors pointed into a scene with two people. The framework leverages the Azure Connect body tracker to track bodies from both sensors. And here are the bodies tracked by the first Connect in blue. And then here are the bodies from the second Azure Connect visualized in sandy brown. And the framework includes tracking and fusion components that leverage these multiple views together and attempt to construct a more robust estimate of the body position by fusing those two views. So in the process, as multiple views are available, these components reason about and resolve occlusions and other small temporal glitches in the Azure Connect body tracking. To exemplify this, let's bring back the initial bodies as tracked by Azure Connect. These light blue ones are tracked from the Connect on the left, and I've visualized also their tracking ID at the top, 102 and 105. And then again, here are the sandy brown ones tracked by the Connect on the right. And during this sequence, as 102 starts moving behind 105, you'll see that they become occluded and disappear. And then later they reappear on the other side, but now they have body tracking ID 107. So when using information from both cameras, the framework performs fusion, and the sequence now looks like this, with the identity of the fused bodies maintained throughout. And this is a pattern whereby we fuse information from multiple sensor views to construct a more robust estimate. And that's a pervasive kind of core tenet in the Situated Interaction Foundation framework. For instance, we plan in future extensions to use basically the same pattern to fuse information from cameras to do better object detection, or from multiple microphone arrays to get even better sound source localization. So there's lots of opportunities for fusion. Now, tracking body pose is, however, only the start for building a deeper understanding of what's going on in your interactive scene. We might also care about the group relationships in the scene. So, picture how you typically stand face to face with someone when you're in a conversation together, or how you stand in a broader circle when it's a larger group conversation. Those spatial configurations are called F-formations. It's a term which comes from the sociolinguistic literature. And in some cases, like here, you actually might stand side by side while engaged in an interaction with a single point of focus. And that spatial configuration is another kind of F-formation. In SIF, we have a model for computing such F-formations from each actor's position and orientation in the scene. And it can handle any number of people, although in this example, again, you're just seeing 2 people in this collaborative cooking scenario. And here you're seeing projected onto the floor there these circles that are showing each actor's position and orientation in the scene. And computed from those positions and orientations is the F-formation that they are both participating in at this moment. Again, projected to the floor here as this irregular polygon representing the shared interaction space of their F-formation. Of course, these F-formations are dynamically inferred continuously over time. We see here the maintenance of one F-formation, then it breaks as the actor on the left moves behind the other actor, and then a new F-formation is established when they get to the other side. And I've already mentioned that the rich streaming representations in SIF involve these historical views that you're seeing represented at the top. The analysis we get doesn't only provide the instantaneous view, but rather at any point in time, the full history of the interaction is available. So for instance, we have illustrated here at the top the historical view of the existence of both people in the scene, along with the F-formations as they dynamically evolve. So the developer has access to information at any point in time, such as when did this person get here, and what was their trajectory, and when was the most recent F-formation established, and so on. While Psi is already very good at dealing with time, SIF introduces a whole other layer of temporal representations that enable efficiently and incrementally streaming this historical view that involve descriptions of temporally extended entities, like people and F-formations, and their properties, like location and so forth. And these kinds of incremental representations have been studied in the spoken dialogue community, and we believe are a necessary fundamental basis for creating systems that are responsive and can create fluid and seamless interaction. So the incremental representation in SIF supports not only filtering, which means the computing the current state of the world based on evidence accumulated so far, but also smoothing, that is changing your opinion about what the past has been based on new information, or forecasting, which is basically guessing or projecting into the future. For instance, in this sequence here, as the person approaches, you can see in the temporal view at the top that a new F-formation is tentatively inferred. The F-formation temporal entity is visualized with this dotted line here in the rectangle at the top in the historical temporal view. And the SIF temporal infrastructure operates with the notion of temporal commitment to implement filtering, where representations of the past might be allowed to change up to some time point. So in this case, the F-formation you see there has not been committed to yet because the inference model underneath is not yet sure whether future evidence might change that assessment. Basically, it's not sure whether that F-formation is real or not yet. And indeed, future evidence does tell the model that the initial inference was spurious and there really wasn't an F-formation there. So it not only ends, it gets deleted from the historical view. So I'll play that forward. And as you can see, and I'm looping it just a few times, but as you see, as the person is actually going behind the other person, the inference model is able to, in a sense, update the past. It realizes that wasn't truly an F-formation because that person was moving behind the other one, and it removes it from the history. Moving forward, a new F formation is detected, and this time this one eventually does become committed. You see the dotted line goes solid, as the inference model believes it has collected enough evidence to say that this F formation was a real one. And this ability to incrementally update the historical picture of our situated context is of course not limited to just inference of F formations, but CIF provides this fundamental representational basis for all entities that exist across temporal intervals with a defined start and end time. So including like the presence of people and objects like you're seeing at the top in the scene over time. And soon we'll be adding more representations for utterances, actions, and activities that have temporal extents and similarly evolve through time. Let's now turn our attention to attention. Attention is another very important construct in interactive and social settings. CIF includes simple models for inferring a person's attention, and we plan to continue to evolve these models over time as well. In the initial release, we plan to use a very simple model based on head orientation, which you can see here represented by this orange ray projected from each actor's head direction. And apart from direction of attention, the CIF perception pipeline also computes the target of attention by intersecting the computed direction with objects in the world. So the target object as well as the 3D target point are identified, as you're seeing here with these red spheres. Of course, like with everything else, all of this is tracked through time. And because CIF provides all this information in a streaming fashion, it's easy to use together with the stream processing capabilities in Psi to compute application-specific quantities. So for instance, here we simply aggregate these points over time to construct a heat map of where attention has accumulated over time on the work surface in front of these two actors collaborating in the scene. Again, this initial model we're showing here is very simplistic. It's just based on the head orientation of each actor. But in the long run, our plan is to extend this representational basis and then continue to refine the accuracy and improve the quality and robustness of the model, as well as of all the other perceptual models in Situated Interaction Foundation. So those are the three main types of inferences we plan to push out with the initial release of Situated Interaction Foundation. But that's just the beginning. We plan to evolve this with many other representations and inference models, such as for conversational engagements, detecting when conversations are happening, and tracking the structure of turn taking. For example, who is talking, who are they talking to, who do we expect will talk next, and so on. Detecting relevant objects, like when they're picked up and dropped off in the scene. Actions and activities, and higher level relationships beyond just F formations between people, but also, for example, relationships between people and objects, like using relationships and ownership relationships. So we plan to extend CIF in a lot of different ways moving forward to include things like this. Now, like I said earlier, one of the central principles here is to make this easy to use. So for example, this is the core part of the main application level code that actually generated much of the data you've been seeing in these visualizations. Basically, you just need to instantiate your CIF application pipeline, add the existence and location of some known objects in the world, and add your sensors. In this case, we had two Azure Connects, and you're seeing here we're using some constants that define the location of the objects and sensors in this specific application. And that's it. You can persist everything inferred by the app and simply visualize, as we've been doing here, or you can plug into the various outputs of people, F formations, attention, and so on, and write your own controllers or application logic that leverages them. And again, the other part of this philosophy here is that all of these inference models are customizable, easy to replace or add to. We know that a lot of flexibility is needed when building these types of systems in different domains. And apart from being open source, we are purposefully designing this to be plug and play, where you can add your own models for any of these inferences and combine them with existing models to increase robustness and so on. So here, for example, you're seeing a couple of lines of code to replace the underlying model for body tracking and to replace the underlying model for inferring attention directions. And it should be just that easy. And finally, Although this initial release will include just a perception pipeline and inferences about bodies, people, attention, and F formations, not only will we extend that perception pipeline to include more inference models about speech, actions, activities, and so on, but we also plan to extend to include other connected pipelines that complete the loop from perception to control to realization and back into proprioception so that the system can perceive its own actions in the world. Because after all, this is called situated interaction foundation, and building systems that can interact here is the ultimate goal of the framework. We've started building out these other pieces internally, but we foresee a lot of fun and interesting research questions on how to build sophisticated controllers and behavior realizers that can fully leverage the rich representations provided by the SIF perception pipeline to create seamless interactions, including those incremental historical views of the context and everything that's happened up to now, where inferences might change not only about what's happening now, but also about what the system thought it was perceiving in the past and then changed its mind about. So anyway, I'll stop there, even though there's lots more detail I could go into about this. But hopefully that gives you a taste of this new framework of representations and components for situated interaction that we're building on top of Psi. As I said, we plan to push out an initial release within a few weeks that includes perception of the constructs I talked about earlier, along with a very simple sample to get you started using it. But we're really excited about continuing to build this out and extend it. And we hope you'll find this interesting and useful. So let us know what you think. We'd love to hear any comments or questions that you might have about it. Thanks. Okay, so I hope you enjoyed that session. I hope you found that interesting about some of the recent stuff we're working on in terms of this new framework on top of Psi, Situated Interaction Foundation. So yeah, feel free to drop any comments or questions in the Q&A chat as always. We can go through those. Let me just reiterate a couple of points I made. So like I said, we are going to have an initial release out hopefully soon. You know, we plan to do it within the next 3-4 weeks. And it will cover basically what I talked about there, the perception subpipeline of SIF, focusing on body pose, F formations, and attention, and deeply leveraging the Azure Connect sensor for now. And then we will continue to push out not only more models and capabilities within perception, you know, around conversation and turn taking and utterances and speech, stuff that we have started working on internally, but need to build up. And then other things that we've also started working on internally that we're excited to push out in terms of completing that loop from control to realization and proprioception. I just want to say that, you know, it will be like kind of a preview alpha. So, you know, use at your own risk. It will, you know, I'm sure there will be some bugs and issues with it if you know, as we get started kind of rolling this out more. But I would, you know, we're really excited about pushing forward on collaborating with people and getting more eyes on it and getting more people to use it in their own research, and letting us know, you know, how they're using it and how they'd love to see it extended and, you know, what kinds of things that they want to add to it. I think that's going to be a really fun area going forward.
There's a question, Sean. There's a bit of excitement, so, but there's a question also about does it need the Azure Connect stream to work, or would it work from a body pose stream from another source, like from 2D images using Compose or Detectron?
That's a great question. So in this initial release, correct me if I'm wrong, Dan, on any of this, but in this, this very first kind of preview alpha, let's call it, we're going to have built-in support for Azure Connect. Right, so that's kind of the main device we're supporting right now. We'll also have more components that kind of support like Connect 2, if that's what you have, or, you know, maybe RealSense. You know, and when you see the pattern, like, it should be fairly simple to extend that, because basically, you know, what you need is some component at the beginning that's just a simple input-output component. It goes, you know, in the Azure Connect case, it takes the Azure Connect's bodies, like the Azure Connect technology bodies, and converts into the SIF representation of a body, which should hopefully be flexible enough to adapt to kind of any technology. But then it's an interesting question to talk about this 2D case. It's something that we've also thought about adding. I want to think about how to kind of support more, because there's a lot of models out there now around 2D body tracking from images. I think if you can at least infer 3D poses and 3D positions from that, and there are models for that too, I know. I think you can then go from that into the world of SIF, because SIF for now is it's like fully in a world of 3D. So all of these representations are 3D, the spatial representations, I mean. So bodies are 3D, objects are 3D. So as long, and we've even experimented with, like, say you just have a face detection result and you have the camera intrinsics. And so you can at least project the face into like a floating head point. And so that your whole body is just a floating head joint. But even that should work. That should be sufficient to at least give an actor some presence in the scene. But it kind of is still in this 3D world. It is interesting to think about like what would be a 2D version of SIF, where like everything you have is in 2D. But I think that would require kind of a deeper sort of architectural shift in some of the things we're thinking about. But it is kind of interesting how we would support that.
Yeah, I was gonna just like to clarify just something you said at the very beginning, Sean. I think you said it, but we're designing this with a view to be very piecemeal, kind of decouplable. So in principle, you should be able to take an open pose body, or like, especially if you have, but like Sean said, the big limitation is the 2D versus 3D, and inject it directly in a SIF perceptual pipeline from where the downstream components will do the fusion with multiple views and all that stuff. So you don't need necessarily to start with an Azure Kinect, but there is this 3D kind of aspect of it that Sean highlighted that I think, at least right now, the data structures that you can inject in kind of have to have this 3D aspect to them, I think.
Because I think it just lends itself well to the kinds of inferences we're trying to make about, F formations, which is a very 3D concept, or, even source of utterances, like, by having this like ray being projected into the 3D scene.
And the physical world is 3D, so
we
cannot get much, right? Like, I mean, we can do a lot from camera, and there's interesting research out there, I think, on projecting from 2D to 3D, right? There's a lot of vision research in that direction. And, sometimes, of course, your sensor is not a 3D sensor, but really the world ultimately is 3D. So I think that's part of that choice, enable us to do more things. There's another interesting question from Chirag. He says, SIF looks really cool, directly pertinent to my current research, going back to yesterday's discussion about transparency in the roadmap for SAI. May I request a similarly transparent roadmap for SIF as well?
Yes, you may.
You can probably commit to that, yeah.
We need to do it. Yeah, I think especially once we have this initial release, and I should say, like, probably people have seen early versions of SIF and even precursors to SIF for a while. We kind of have gone through different iterations of building up the architecture and some of the representations behind this. But I do think we're at a place where now we feel pretty confident about some of the, like, there are some deep representations and infrastructure and kind of libraries we're building underneath just to purely deal with spatial things, relative positions and absolute positions and coordinate systems. And then some deep infrastructure and I just kind of hinted at it, but some pretty deep and I think really kind of powerful APIs and libraries for dealing with these temporal incremental streaming entities. And I think that's really evolved kind of especially over the last year of us working on SIF. So I think we feel really, we're at a good place to kind of release this alpha now. And I think once we have that out, Chirag, I think we can commit to having a kind of a more transparent roadmap of what are the next, what's always the next piece that we're going to try to add to that. And it'll be partially driven on, some research interests that we have and projects we have, but again, I think also once it's out there and other people are using and looking at it, hopefully that can also be partly kind of dependent on other people's interests and what they want to use it for and what they're would like to add to it. So I really hope that it can grow into not just us telling you what we're going to do next and you wait, but like, you know, we can kind of collaborate with the community on building it up together. And then Willie had a question above about, for the components doing inference, will you be releasing the full source code, or will there be components that call Azure services? Like, can all of this be run locally without the cloud? Yes and yes. I mean, basically, we want to be able to have different options for kind of all of these components underneath. So, you know, like what's going to be out right now, I don't think there's any requirement for Azure services for the stuff we have now. It is, you know, kind of deeply leveraging the Azure Connect body tracker. But all of the components that we're writing, especially any of these kind of heuristic components about computing F formations and computing attention, it's open source. That'll be all, you know, open source for you to look at. And like, I think that'll be important for people to see the patterns of the inputs and outputs and kind of how these representations are built up. And then hopefully we'll have enough of those, you know, fully open source components out with good patterns that people can then write their own and focus on their own technologies and really kind of focus on the piece that they're most interested in.
Yeah, and this is also a piece where I would say, like, exactly we're, like Sean said, we're trying to put kind of a set of patterns that we believe would be useful in place. But again, it's a component ecosystem almost story, right? Like someone might be using OpenPose or other, and we want to construct it as a tool for research where people can drop in and out of components and use whatever they think is more useful. We're focused a lot on creating the right kind of representation at the base and kind of baseline architecture, and providing an initial set of components to which you can do everything kind of locally. Now, you know, and then those will evolve, right? In different ways, people can bring their own, we'll continue to evolve them and so on. I would encourage people to think about contributing in that space as well, because I think it'll get interesting once we have different flavors of, you know, some of these perceptual components and can start comparing things and so on in end-to-end systems, as opposed to just kind of boxes and piecemeal. I think that's one of the affordances that we're trying to also create here.
Yep. But yeah, and I think to your point, Willie, about like cognitive services and Azure services, like I think it'll be possible to run without them, but also it'll be a benefit that you can plug those in if you want, in the middle of it. You know, you have everything maybe locally except this one, I don't know, speech recognizer that's running in the cloud, or, you know, some aspect that's running in the cloud. And it should be just as easy to plug that in as anything locally. You know, you might have higher latencies coming in and out of that component, but at least Sai will be able to reason about that and to deal with that. Z had a question. One challenge I have working with a mixture of Connect 2 and Azure Connect is that the body objects are very different with different joints. Is there an independent body object inside to represent people? So that's a really good question. So we have, I mean, yeah, we've also, you know, dealt with this issue of having, you know, Connect 2 bodies that have a different joint, you know, set of joints and skeletal structure than the Azure Connect, mostly because the Azure Connect just introduced a lot more joints. And the way we kind of go around this is we you know, we have a body joint type class that you can extend, you can derive from. And so any, you know, whatever your technology is, you can derive from that class, and you can define that this is the set of joints that are relevant for my body. And then, you know, this kind of points to this tension we have in SIF sometimes. It's like we have to provide some kind of representational basis, but make it flexible enough for people to extend, or we have to make some commitments. You know, so if we thought a lot about, like, you know, how do we want to define a body? Okay, let's say that a body is a skeleton, so it's got to have some number of joints and connections between joints. And we say that's what a body is, but we're totally agnostic to what's the name of those joints, what's the topology of, like, how are they connected. That can be, you know, completely defined by your specific version of the body type, and it'll flow through the system totally fine. So we have examples internally of, like, having Connect 2 bodies combined with Azure Connect bodies, and even, like I said, like this case where it's a one joint body of just like a floating head in space, because the way you sensed it was from a camera doing face detection. So those all show up in SIF as just bodies. They just happen to have different numbers of joints. But that also points to a very interesting kind of open question we're still thinking about how to solve, is when we do this whole fusion thing, we're talking about tracking and fusion. It's a lot easier to do fusion for multiple sensors when they're the same sensor that gave you the same representation of the body, right? So if we have two Azure Connect bodies that we're fusing together, it's a lot easier when we have a one-to-one correspondence on all the joins. When we start fusing Azure Connect with Connect 2 bodies, let's say, or with floating head joint bodies, it'll be interesting to think about what's the kind of best and most robust way to do that. I think we're still thinking about what might be the best approach there. I know other people have thought about this in other kinds of ways. So I think we'll have again like an initial example and pattern for doing this kind of fusion. And again, we'd love to chat with people and kind of collaborate on how to do that in some of these more heterogeneous cases. Is there anything?
There's one other question. There are other tools in the first release that combine audio.
Do you want to take that, Dan?
So yeah, I think the short answer is not in the first release, probably most likely, but we hope to add them shortly after. I mean, in our work, Sean and I have done a lot of work in the past where, we focused a lot on spoken language interaction in physically situated settings. So definitely we've worked a lot with audio and utterances and multi-party turn-taking models, floor control models and so on. So we're hoping to extend. I mean, we are planning, I'm just hoping we're planning, and we've done that kind of work in the past. And we're partly building us as a tool that we ourselves will use in future systems we're developing. So it's definitely coming down the pipe, but it's also not in the first immediate release. And the other thing I would say to that is with all of these, as we push it out, like Sean said, we're pushing it out in some sense early. We want to engage with the community. We want to get feedback and, get even contributions. So that also means, the very first releases we'll have and the early models, even for audio, don't expect them to be super stellar in any way, right? Like it's like we're going to start by pushing simple heuristic models for some of these things, like turn taking, and then probably evolve them over time. But the goal is really to simplify the perception problem, especially for people that don't want to deal with all of that, that want to build interesting applications on top, right? Like the ideal, in some sense, there's multiple users here potentially, but, and Sean alluded to this in the talk, right? Like on one end, you can treat it hopefully as a black box one day and say, I have these sensors, do all this perception for me, and let me build a cool application on top of that. On the other end, if you're a researcher, you can go and tinker with a research problem you're dealing with, but still be able to evaluate an end-to-end system. Because I think a lot of the problems, like the state of AI today is with a lot of like very deep wedges where there's a lot of kind of progress focused on metrics on individual problems. But when you try to put all those things together end-to-end, and that's what Sai is trying to do, the story is not that good yet. And so I think it's more important that we evaluate more often in end-to-end systems, these AI technologies. So, and I think that's another thing that with SIF we're trying to provide a basis for.
Yep. I know we're going a little long, but there's one more question here that I really want to talk about because it's so great. So they asked, how long does it take to decide to commit an inference? If we're feeding a robot action in real time, how does it control not to take actions on inferences that are still uncertain? And that is a phenomenal question because I have no idea. I don't know, and I really want to find out. I think that's to me one of the most kind of exciting research problems that I think we can go into because of all this notion about having these temporally extended entities that are incrementally update. There's this notion of commitment. Have you committed to it or not? And it'll open up, I think, lots of interesting kinds of controllers where maybe the robot did take an action on something that was not committed, but then it gets a signal that, oh, it was deleted, like in that affirmation case. Actually, there was no group there. And so you could imagine doing things where the robot like apologizes for its action, or it says something like, oh, sorry, I thought you were in a group together. And it kind of moves on from there. Because that's kind of what people do, right? Like we kind of take these actions. And then when we update our picture of how the world actually was, and we like reflect on how that matched our mental model of how the world was, in the past, we can kind of reconcile those things and do repair. And there's all these mechanisms for that, like in interaction. So I think it's a really cool space to explore. I think, you know, to collapse it to what, you know, what you do now is basically you could just assume that everything was committed, kind of ignore that commitment thing. And that would basically collapse to how you write controllers right now, right? Because you just have this instantaneous view. And if you just ignore the fact whether something's committed or not, that would kind of collapse to kind of the simple way to write, not simple, but sort of the standard way to write controllers now. But it's interesting to think about how to extend controllers to take into account this more complex historical and incremental picture of the world. And it's, like I said in the talk, like this has been looked at a little bit in spoken dialogue systems. Like a lot of this kind of was inspired by spoken dialogue systems and doing incremental utterances. And there's a lot of techniques from that realm I think we can draw from. But it's interesting to think about that in this full kind of multimodal space too. I don't know if you want to add anything to that, Dan.
I think that was great. Yeah.
Okay.
Completely agree.
Yeah, it's an exciting question because I don't know the answer. I want to find out. Cool. Okay. Well, yeah, I hope you guys enjoyed that. Stay tuned for that release. And I think with that, I think that brings us basically to the end of the workshop. So I think we can wrap up for the day. We don't have too much in terms of closing remarks here. But we just wanted to say, first and foremost, thanks for coming. Thanks for being here. Thanks for spending some time with us and learning a little bit about kind of the basics of Psi, how to use it, what it's good for. And then today, some of the new stuff, the stuff that's coming down the pipe. I hope that got you excited. And I hope that you want to kind of stay involved and collaborate and use Psi going forward. So I think to that end, stay tuned to the GitHub repo. So we're going to continue to post new updates to GitHub. We're going to obviously push new releases to GitHub, but we're going to post new updates to there's like a what's new section on the main page. Don't hesitate to get engaged, make issues, and on the GitHub issues. There were some great ideas and comments yesterday in the panel discussion on other ways that we can engage and other platforms and systems that we can use. We're going to look into some of those things and follow up with that, but I think for now, we'll continue to use the GitHub page and GitHub issues. So please, not only make bug reports there, but let us know about kind of what you're using Psi for, if you have any feature requests, any things that you'd love to see. Just generally don't be afraid to make lots of issues there. We'd love to talk to people there. And then just as a reminder, if you haven't already, please take just a few minutes to fill out the post-event survey. That'll help us know kind of how we did, how did the workshop go, and what did you like most. Yeah, and do you want to add anything?
Thank you everyone for coming, and it's been a great couple of days. We had a lot of fun. There was lots of great questions, and like Sean said, I hope you guys will stay in close touch with us through the GitHub, and I'm looking forward to the next event and to see where we can take this framework together.
Absolutely. So thanks for coming, everyone. Hope you had a good time, and we will see you down the road. Bye.